we can start the next topic, that's equation of state models. Here we will go through the fundamentals of the equation of state model, so when tomorrow when we'll be developing the EOS model, we will know what is an EOS model, what it is composed of, what does the different parameters mean, when we will look at the equation of state, the two tables that Matthias mentioned on the first day, component properties table and the binary interaction parameter table. So we will know what do they mean, what each component property means, and how the different properties affect, for example, the phase behavior. So in this presentation, we will go through like the simplest equation of state we have for the gases is the ideal and real gas law. We'll start with that, and then we will jump into the cubic equation of state models, and there will be a bit of history, and Curtis can talk about the interesting stories about the history, of course, and then we will see how the equation of state models can be used for single component, and then we will have this volume shift factors. We will see what are these and why do we need them in the EOS models, and then we will go into more complicated phase behavior where we have multi-component systems. You'll see how the EOS models are applied to such systems which we generally see in our petroleum system. So as an introduction, these are just the book definition of equation of state. The examples are like the gas laws, as I said. These are the simplest equation of state. You have cubic equation of state model that we generally use, Peng-Robinson, SRK. Those are our cubic equation of states. And then we also have some non-cubic EOS or soft EOS models that are not discussed in this course. So the ideal gas law, everybody knows, PV equals to nRT. No need to have a long discussion on that. In the gas law is applicable to ideal gases, like very low pressures and high temperatures where the gases behave ideally. And then we have a real gas law, which where we have this gas Z deviation factor, or the gas Z factor, which accounts for this non-ideality of the gas. And we know that Standing Cards, who have developed this chart for the gas Z factor, that can give us very accurate values of the gas Z factor, and that's the only thing you would like to know for the gases to describe the PVT behavior of the gases. So the gas Z factor is the fundamental property in describing the phase behavior of the gases. For the liquids, we only have this PVT equation. That's the isothermal compressibility, describing the single phase pressure, volume, and temperature relationship for the liquids. So really, what we need a PVT equation that is applied to both gases and liquids at the same time, and that is achieved by this cubic equation of state model. So it's the same equation of state, or same equation that describes the pressure, volume, and temperature relationship for both gas phases and liquid phases. And in terms of the Z factor, we can write this equation like this. So this is why it's called cubic, because it has this cubic power. So the highest power in the equation is this cube here. So that's why these are cubic equation of state. And then in the equation of state, we have different coefficients for each of these polynomial terms. So it's 1 here, A2, A1, and A0. And we will see, like, for example, when we'll go through the different EOS models, Peng-Robinson, SRK, or Redlich-Kwong, like how we can calculate these coefficients, which are written here. So these will be different for different equation of state models, and they are mainly function of pressure, temperature, the composition, and the component properties, and they are formulated differently for different equation of states. The other important comment is that here you see the cubic equation of state model written in terms of the Z factor, but this can also be written in terms of the molar volume, where we know that the Z factor can be equated to the molar volume. So this V is actually the volume divided by the moles. So that's the molar volume. Generally, the EOS models, they are written in terms of the Z factor, because when you solve them in any PVT package, you generally prefer to solve them in terms of Z factor because it's more convenient and more efficient. So that's why here you see in terms of Z factor. But when we will discuss the different equation of state models, you will see that those are proposed in terms of the molar volumes, and then you can easily transform them into the Z factors for thermodynamic calculations. Yeah, so again, the cubic equation of state models, they can be applied for both liquids and gases, and also it can be applied for pure components, and also mixtures with some assumptions and mixing rules that we will see later on in this PowerPoint. Most common equation of state models that we are generally aware of is the van der Waals. That's the first cubic equation of state model developed in 1870s. Then Radley-Kwong developed or modified actually van der Waals equation of state model. So this is, you can say, this is kind of a parent cubic equation of state models, and all these models that came later, these are just modifications to van der Waals for different applications and purposes. So van der Waals, that was the first cubic EOS in 1870s. Then Radley-Kwong modified it for, we will see, then we will go through that, for mainly for gas processing. Suave Radley-Kwong EOS, it's actually the same EOS as Radley-Kwong, but with more generalized correction. We will see also later what are those corrections, and the applicability of the SRK EOS. It was in 1972, and then 1976 was Bang-Robinson EOS. Yeah, so we will discuss these EOS more in detail later on. Yeah, so first we will see how this cubic equation of state models, the different ones, SRK, RK, Bang-Robinson, how they are applied for single component, and then we will move to the more complicated multi-component systems where the same EOS models are applied, but with certain mixing rules. The van der Waals equation of state. So yeah, again, it was the first cubic EOS. The two parameters in the equation of state model are the A, this is a small a and small b, and you need these two constants to relate the pressure, temperature, and the volume for a given component. So if you know A and B, for example, for water, you can calculate, for example, at any pressure and temperature, what's the volume of water, for example. And A and B, so A is generally called as the attraction term, and this is the repulsion, the B parameter. And what you can also see from that equation, that if you increase the pressure to infinity, this expression here, this equation here, the volume will become the B term, and that's the minimum volume on a molecular scale. So that's the minimum volume that a component can have at any at these infinite pressure. So it's not the zero volume, which is the assumption in the ideal gases. Also, like if we decrease the pressures and if the pressure tends to be zero, then you can see also from this equation that this equation will transform into P equals to RT over V, which is the ideal gas equation, PV equals to RT. And that's something we know that at very low pressures, gases behave ideally. So those are like two special cases of this cubic EOS. Yeah, so just to be aware that the A and B, these are constants, and these should be constants for a given or a particular component. These are just the units, for example, for the two parameters, and this should be fit Q actually. So this has B has the same unit as the molar volume. So now the main question is like, if we want everybody now, and yeah, now you know that the cubic equation of state model, to make use of the cubic equation of state model, at least there's van der Waal, you should know the A and B values for a given compound. So if I ask you, like, for example, if you have water, and if you want to know the value of A and B, for example, for water, how would you come up with those values, for example, for water? Any suggestions from the participants? Anybody want to share some ideas here? And so if you want to know what are the best values that we should use for A and B, for example, for water, to use that van der Waal equation, how can we come up with that? Yeah. Okay. So like one way of doing it, for example, is that that's like the general way we usually think, is that if you have some kind of data measured for water, for example, and we have a lot of data, phase behavior data measured for water, we have steam tables, vapor pressure is measured as a function of temperature, we have saturated liquid and vapor densities at different temperatures. So we have a lot of data measured for water as a pure compound. We can use that data and try to find out the best value of A and B by matching or using the van der Waal equation of state to better predict all that data. So doing it. But one issue in doing that is that first it's a lot of work. Like you will be using a lot of data and try to tune your cubic equation of state model and come up with a single value of A and B. And the other is that if that work is, for example, done by Matthias or Curtis or me, we may come up with different values of A and B, because that tuning of the cubic equation of state and the tuning of A and B value will depend on which data, like when I'm doing the regression, which data I'm weighting more, or Matthias thinks is more important, for example, or Curtis thinks is more important. So we may come up with different values. So van der Waal, he has this great idea of finding the unique or specific values for A and B for any given compound. And what he said that if we like draw pressure volume diagram for a given component, so we know that it looks like this line here. So that's at given temperature, where the temperature is less than the critical temperature of the compound. That's how the pressure volume diagram looks like. And if we continue to increase the temperature and make the same pressure volume diagram, we know at critical temperature there is only one inflection point where we have both the saturated liquid and saturated vapor phase coexist. So that's the critical point we have, and this is the phase envelope. That's this dotted line here. So what we know about this this critical point here on this pressure volume diagram, so that's just a higher greater than the critical temperature. What we know at the critical point, that we can write the van der Waals equation like this, right? So this is just applying the equation at the critical point. So P is replaced by the critical pressure, temperature is replaced by the critical temperature, volume by a critical volume, and we have the same A and B. The other thing we know about this critical point is that if we take the derivative, the first order derivative of this equation with respect to volume, then it should be 0 because there is just one inflection point here. And the second thing about the critical point is that if we take the second order derivative, that should also be 0 because now after the critical point, it's this function, the pressure volume function, is monotonically decreasing. So we know these three things about the critical point. So now we can, with these three relationships or equations, we can develop three equations with only two unknowns. So we have A and B, which are the unknowns, and we have actually three equations to solve for. So now this is if we can solve these three equations in different ways, and we can come up with three sets of A and B values. So we can solve, for example, the first two equations and come up with this A and B, which is the A and B from the critical volume equation and the TC equation. Same, if we can get the A and B values from critical volume, critical pressure, and critical temperature. And these will be the different values of A and B. So what van der Waals suggested is that van der Waals said that we can use the value of A, B from the critical conditions. So the critical pressure and temperature. And he said that he just neglected the A and B that could have come from the critical volume. So we got the A and B values here. If we solve, for example, these two equations here, the TC equation and the PC equation, we get these values of A and B. And we will see later on what happened, what was the consequence of neglecting the critical volume term, and how can we actually correct for that consequence. That's something we will see later. So these are the A and B values for any given compound, and you can see from these equations that if you know the critical pressure and temperature for a given compound, you can calculate A and B, and that will be a unique value of A and B for a given compound. So for example, for water, we know what's the critical pressure and critical temperature. So knowing that, we can calculate the exact value of A and B. And that should be unique to water. So if we now know that A and B are defined by this, then we know that VC is equal to actually 3 times B. So the VC now, if we replace the value of B that we have calculated before, so VC now will become 3/8 R times TC over PC for a given component. And if we calculate the critical Z factor, which is simply PV equals to MZRT, and each pressure, volume, and temperature are critical properties, then we can find out that this is just a constant value, 3/8, the critical Z factor. So critical Z factor in this van der Waals equation of state model is 0.375, and you can see that it's just a constant value. So it's not a component dependent number. It's just fixed for all components, and that is actually the consequence of neglecting the critical volume term. So when we neglected the critical volume term and we only used the TC and PC, that's what happened, that now the critical Z factor is fixed for all components, and that's not the case actually. So if you look at, for example, methane, it has a critical Z factor of 0.28, and generally if you go towards heavier components, it decreases. So this is actually far removed from the hydrocarbons that we are we are generally interested in. And van der Waal, he was not like when he was working on the cubic equation of state model, he was not interested in using the EOS models for the petroleum mixture. So that was not a big deal. And but what happens with this, like yeah, so these are just the forms of the van der Waal. So this is the van der Waal equation. So that is now the coefficients. So b plus 1, that's the coefficient for z square, and a is for z and ab here. And the way we define a, the coefficient here is the small a times pressure over RT square. And we already know what is the value of a, so we can bring that. So it's to reduce pressure to reduce temperature. And same goes for capital B. Now it's a function of pressure and temperature, and also the small b. And these numbers here is 27/64. That's a constant number, and this is also constant number. So this is the omega A and omega B. So if you, like we will see later on, this is omega B and this is omega A. So these are generally termed as omega A and omega B, and these are constants in for all the components in a cubic equation of state model. And these constants, the values of these constants will vary from one equation of state model to another. Yeah, so this ignoring the critical volume term to derive the value of A and B, the component VC now is defined by the 3B, 3 times B, and the ZC, the critical Z factor of all the components have become constant. And this has led to, like, if you start calculating the densities or molar volumes, the liquid phase molar volumes at all conditions, so it leads to high deviation compared to the lab data, and the liquid densities were predicted very low. So like if we use, for example, the van der Waal equation of state with the A and B given by the van der Waal, what we will find out that if the liquid phase densities, they will be predicted about like 40–50% lower compared to the lab data, because the molar volumes are predicted higher because of the fact that the ZC value is about 0.375, which is quite higher than the normal expected ZC value of these hydrocarbons that we have, which is starts from about 0.28 for ZC of C1, and it goes lower. And it mainly affects the liquid phase densities and not the gas phase densities, and that's something we can see on this plot. That if you plot pressure volume diagram, so this black line is the expected phase behavior of a particular component. Maybe it's water. We can just say it's water, for example. That's the expected or the lab measured, for example, data. And if we use the cubic equation of state model, that's how it will be predicted. It will predict the right, for example, the critical point. So that's for example, this is the critical point. So this is gonna be PC, and we are doing it at TC. It is gonna predict the right PC and TC because those are the inputs in the equation of state model to get the A and B. So it should predict the right critical temperature and pressure, but the critical volume is gonna be with an equation of state model, it's gonna be much higher than the expected value, and this is gonna drive all the liquid phase. So here on the left side of the critical, we have liquid phase. On the right side of the critical, we have vapor phase. So on these liquid phase densities, they are gonna be much lower because the volume is higher, so about 30–40%. But the gas phase densities are not much affected because like small difference in the volume here is not gonna translate into much error because the volume itself are much higher. Here the magnitudes of the volumes are lower, so small differences will end up into a large error. Okay, so now we jump into the Radley-Kwong equation state model, which is kind of the first EOS model where people actually started using the cubic EOS models for petroleum applications. Any questions until now? Anything that's not understood, or somebody wants to know more about something? Yeah. Okay. Yeah. So Radley-Kwong equation of state. Um, yeah, Kurs, do you want to speak out a bit about the history, like what was happening at that time, and yeah, just
49 was when Radley-Kwong was presented, and that's the same year that Muscat and McDowell published this flash calculation for separator design and petroleum applications, but using fixed known K values. But basically, this was the age of computers starting to be used in science, engineering. So that's the backdrop for the Radley. I think development became very important, but is related to the post-war, the computers starting to be used.
Yeah. Yeah, and the main thing that Radley-Kwong and their group was interested in is to get the like they wanted to use the cubic equation of state model for to get better phase behavior of these lighter components, because they were working on this gas processing calculation, and they were interested in calculating the accurate liquid yields at surface. So they were very interested in getting very accurate phase behavior of these lighter components, which we usually see at surface and they end up in the gas phases. So yeah, so this was the objective for them, to modify or come up with a cubic EOS model that accurately predict the C1 and lighter hydrocarbon phase behavior more accurately. So they proposed two modifications in the van der Waals equation of state. These modifications are highlighted in blue here. So this was one modification, that's this alpha term as a function of reduced temperature. So that was one modification. The other one was this term here, so they added in the denominator with v square. And the two modifications have two reasons. And this whole term here, a times this alpha, the correction term, is now written as a of rk. So that's Radley-Kwong a, that's being modified from the a value given by the van der Waals. So yeah, before we go into the reasons of these corrections, this is just how the equation of state looks like in terms of the z factors, and you can again see that this coefficient is a bit different than the coefficient that we saw in the van der Waals. And this capital A is equal to, it's again the function of pressure and temperature, and then the small a, and then here is the small b, and then the small a of rk is actually the same as the small a of the van der Waals equation, but then we have this alpha, the correction term, and then we have again the b, and then this omega a and omega b will have different values. So these are the values of omega a and omega b in the Radley-Kwong equation. And then alpha, what they propose that alpha, the correction term to this a term here, is just 1 over, that's just 1 over square root of the reduced temperature for the given component. So what the reason why this correction term was introduced, it was to improve the phase behavior, or like the vapor pressure diagrams of these lighter components, C1 and lighter hydrocarbons, because they were mainly interested in getting the right phase behavior of those components. And this second modification of adding this VB term in the denominator, that was to get better liquid phase densities of these lighter hydrocarbons, because if you calculate the ZC value of the Redlich-Kwong equation of state, you will find out that it's ZC is equal to 1/3. So ZC is equal to 1/3. That's 0.33, which is much closer to, for example, you look at for methane, it's 0.28 somewhere. So you can see it's much closer to the methane critical Z factor compared to what we had in the van der Waal, where it was about 0.375. So that's the van der Waal, and that's the Redlich-Kwong. So getting more closer to the critical Z factor of these lighter components, giving it helped to bring in line the densities better, and but still the liquid phase densities of the heavier components, which they were not mainly interested in, they were underestimated. But and also the phase behavior, like if you look at the vapor pressure curves, they were also not satisfactory for these very heavy components, because this alpha correction term, which is very simple, like 1/√√ of TR, the reduced temperature, it was not very reasonable for these heavier hydrocarbons. So after the Redlich-Kwong equation of state model, Suave, Curtis, do you want to say something here about who was Suave and like why he came up with a different?
Well, by, let's see, the early 1970s, I think the SRK was published. And by then, much larger and faster computers were available. And the processing industry, chemical engineers, started using computers to really do optimal design processing for basically optimizing the processing of more valuable products like gas liquids. Mm. And Suave is Italian and did this work with the intention for it to be applied to petroleum applications, mostly on the top side. Just as a comment, Redlich was originally born in Austria, I believe. He fled just before World War II to the United States, and eventually started working at Shell, where he met Kwong, who was a Chinese-born who moved with his parents early to the United States, and they started working at Shell, I think, more or less the same time, just before or after the war. And in 1949 came with this Redlich-Kwong equation. And then it was greatly enhanced by Suave, specifically in its ability to predict accurately the vapor pressure curve of individual compounds. That was absolutely the big kind of quantum leap that Suave introduced. A lot of people were trying to do it in the late 60s and early 70s, and what he did was won favor because it was simple, it was very accurate, and it was pragmatic, and then once people started using it, they just continued to use it. So it was, once you get vapor pressures of individual components as a function of temperature, getting the K values of the same components in mixtures was trivial, using the fact that K values were inversely proportional to pressure if you knew the vapor pressure. So you basically could get accurate K values for all components in natural gas and petroleum systems at pressures less than about 100 bar, 1,000 psi, just by knowing that the vapor pressures were predicted accurately. That was the big development by Suave.
Yeah. Very good, and that's exactly what why we discussed all these concepts before, like the K values, the dependency of K values on vapor pressure at low temperature, low pressures. So we discussed this earlier, that the K values at the low pressures, they are mainly function. If you talk about mixtures, K values are mainly function of your vapor pressure and the pressure and temperature. And if you get the vapor pressure right, it means that you are getting K values right for the different components at pressures and temperatures that are on the lower side for this top side processing facility type calculations. And as Curtis said, that the big side of this Suave equation of state, SRK, it's actually the same, exactly same equation of state model from Redlich-Kwong, but there is an additional correction that we will see. We did not change the fundamental form of the Redlich-Kwong equation of state, but it helped predicting the vapor pressure curve for all the components and not just the very light C1 to very light hydrocarbons component, right? So, and what he did we saw that in the Redlich-Kwong there is this correction term that's alpha that's added to this the term A. So he actually so this alpha, it was in this in the Redlich-Kwong, it was a mainly function of the reduced temperature, but he generalized that alpha correction term to be applicable to all the components to get their vapor pressure correct, and we will see in more detail how that was done. So yeah, so here it's exactly what is explained here. So what he started doing, he started plotting the square root of alpha versus square root of the reduced temperature for the known components. And what he was actually doing, so here you see that you have 3 points. So for example, this is methane, for example, and we know that for example, for methane, we have quite a bit measured vapor pressure data. So what he was trying to do, he was trying to use the Redlich-Kwong equation of state model, and he started calculating what is the alpha correction or what is this alpha value needed to get the right vapor pressure at different temperatures. So at this temperature, what is the alpha value that requires to calculate the right vapor pressure? Same goes at this temperature and this temperature, for example. And then and it's just a straight line. And then he started calculating the slope of this straight line. So at TR, that's the reduced temperature, which is, that T over TC. So at TR is equal to 1, where we know that the temperature is equal to critical temperature, there is no correction. So alpha is equal to 1. You see alpha is equal to 1. And the main reason why there is no correction at the critical point is that critical point is the input to the EOS model. So you provide these two numbers in the EOS model, TC and the critical pressure. So that has to, at critical pressure or at critical temperature, the vapor pressure has to be the critical pressure from the cubic EOS, because that's the input. So there was no correction at this point, and then you started having more and more correction as you go away from the critical point. And this was just a straight line, and he was trying to calculate what is the slope of this straight line for the compounds where we had the data. So
just a historical comment that he found this relationship between the correction term alpha and reduced temperature, basically plotting square root of alpha versus square root of reduced temperature, produced a linear trend. Once he had done that for a few compounds and found that it was general, I don't remember which compounds exactly he tested this dependency on, but it apparently worked for for a wide range of compounds, from hydrocarbons to non-hydrocarbons, water, etc. Once he had that relationship, then all he required to find the slope, M, of a given compound was a single vapor pressure point on the vapor pressure curve. And what he used was the vapor pressure that was known experimentally for so many compounds at 0.7, 70% of the critical temperature. And the reason that vapor pressure was known and for a large number of compounds is because there was a guy named Pizzer who had introduced the so-called acentric factor as a term to quantify the kind of the shape of the vapor pressure curve. And it relies also on the 2 points, the critical point and the critical temperature, as being 1 point on the end point of the vapor pressure curve, and then the vapor pressure at reduced temperature of 0.7 was the other point. With those 2 points, you can compute the acentric factor. So what he then did is he just simply went into the tables with acentric factor, found the vapor pressure, and then he found the correction term alpha to match that vapor pressure, and then that gave him the value of M for very many compounds. So that's the method that was used by Suave. Now, apparently, and this I didn't know historically, Jürgen Molderup, who wrote the book with Mikkelsen, he told me just recently that Pang and Robinson, who used the same form of this alpha correction term, and they'll all talk about it here in a minute, they didn't do it that way. They basically fit the vapor pressure curve of each compound with multiple points to get the value of M, not just using the 1 point from the acentric factor. What Jürgen Molderup claims, I don't know this for myself as a fact, but he claims that the correlation developed for M and the value of M and how that extrapolates was better developed using just a single point than using a series of points. Anyway, the main contribution, I think, of Suave was finding this functional form, being general for all compound types, and second, to then easily compute the value of M and tabulate it for very many compounds based on the known acentric factor. And so that's just a historical note.
Oh, very good. So, yeah, Curtis, thanks for sharing this. I did not know that also. Yeah. Okay, so yeah, so what Curtis is saying here, where's my pen? Okay. So what Curtis is saying that when Suave he started plotting that data, he found that there was a linear relationship between the square root of alpha versus square root of the reduced temperature, and M was the slope. And then he started calculating the slope for many different compounds, where he had the data with at least two pressure points. So one was the critical point, and the other was the critical one. The other was the vapor pressure at the TR, the reduced temperature of 0.7. That is, we will come back to that, and we will start discussing the eccentric factor. So he started calculating the slope with just 2 points on the vapor pressure curve, and so we can just come back to that. So this was the equation that he came up with to calculate, to know the value of M for a given compound, which is a function of eccentric factor, which you will see in the next slide. What is an eccentric factor? But what he found that when he started correlating the slope of that correction line with the eccentric factor, it was a very good with very good function being fit. So yeah. So yeah, here is the this discussion on the eccentric factor. So eccentric factor is defined, is just a term given to this expression here, which is the log of the vapor pressure with this star, and this is the vapor pressure at the reduced temperature of 0.7, which is 0.7 of the critical temperature. So temperature is 0.7 of the TC, which is close to the critical point. So if you look at this figure, so here, for example, this is your critical point, and then here, this is your vapor pressure star, which is at the T of 0.7 TC. So that's one other point that you can have on the vapor pressure, and then you have a boiling point here. So, and what actually eccentric factor is, so if we take, for example, if we have smaller compounds like, for example, methane, which are more spherical, you will see that the eccentric factor is more close to the zero value. As we go towards more complex and heavier compounds, the eccentric factor tends to go towards value of 1. And if it is 0, it is telling you how much, what is actually the slope of the vapor pressure line near the critical point. So how rapidly the vapor pressure declines near the critical point. So here you can see for two components, here for just illustration purposes, we are assuming that the two components have the same critical point, just for the illustration purposes. But at this temperature here, how rapidly is the decrease in the vapor pressure? So here the vapor pressure has decreased to this value 0.1 of the critical pressure, and here it has decreased much more, which is 0.01 pc. In that case, the eccentric factor would be a 0 value. For this compound, it would be a value of 1. So next is the Peng-Robinson equation of state. Yeah, so in SR, just to summarize, Redlich-Kwong, the van der Waals equation of state, the cubic equation of state, was the first equation of state with two parameters, A and B. And to calculate A and B, you need the TC and PC of that compound. Then there was this Redlich-Kwong equation of state model. To use that EOS model, we again only need the critical temperature and critical pressure of each compound. But then this Suave, he came up with an equation of state model with a more generalized correction, this alpha, to the cubic equation of state model. And there we saw that now we need another component property, which is eccentric factor, which is this guy here, this omega, represented by omega sign here. So now we need TC, PC, and eccentric factor, three properties for a given compound to do any EOS calculation. So still, the cubic equation of state model is defined by two parameters, A and B. But to calculate this A term here, we need we also need the eccentric factor, because the eccentric factor gives us the slope of the straight line correction, and that the slope of the straight line correction gives us the alpha term that's required to correct the A value to get better vapor pressure. So we need three parameters in the component properties, TC, PC, and eccentric factor. And then that's the last and that's equation of state model, Peng-Robinson, and they were Canadian in the Canada, where they were mainly dealing with the heavy oil, and they wanted to get better phase behavior for the heavier fractions, and also the better liquid densities for those heavier fractions. So yeah, so this was the equation of state model, and then they have as Curtis mentioned, that they have a new alpha. So the alpha correction term was different than the alpha correction term that was given by Suave for the Redlich-Kwong equation of state model, and one reason why they had to change their alpha correction term is because now that they propose a new fundamentally different cubic equation of state model with additional corrections to the smaller volume here. You see that these are different than the Redlich-Kwong equation of state model. So when they changed the entire equation of state, the cubic equation of state model, they had to come up with new alpha correction term, which predicts better or equally better vapor pressure curves for the individual components for all compounds compared to the SRK equation of state. So these are just again, so alpha term, again, it's a straight line relationship with respect to m, but they had to come up with these m values. And as Curtis was saying, that this m value, the slope of the line, Redlich-Kwong, Suave, he found out these value of m from 2 points on the vapor pressure curve, one being the critical point, the other being this vapor pressure at 0.7 Tc. But when they were determining these m values as a function of a center factor, they tried to match all the data that's available for a given compound in terms of the vapor pressure. And they have two relationship, one for a center factor of 0.49, less than 0.49, the other one is greater than 0.49. So if you compare the two equation of state models, Peng-Robinson, SRK, you can see that so like this is methane vapor pressure, this is pentane vapor pressure, and they are like on top of each other. So in terms of the accuracy for individual component vapor pressure, there is almost no distinction between the two equation of states. Yeah, so one big challenge in the cubic equation of state model was to predict the accurate liquid densities, the liquid phase densities. And that's again, it comes from this fundamental problem that we ignored this critical volume term in defining the value of A and B, and that was proposed by Van der Waal, and that brought up this fundamental problem, the cubic equation of state model, that the oil phase densities with SR Peng-Robinson equation of state model, those were not satisfactory. So the liquid densities were overestimated for all the compounds, and Peng-Robinson equation of state model was better for liquid densities of the heavier compounds because they were mainly interested in those. For the heavy oils, SRK SRK equation of state model was better for lighter hydrocarbons. So that's something we can see here. So this blue line, this is SRK, Peng-Robinson, and you can see that the SRK is better, for example, for methane compared to this Peng-Robinson here. And here SRK equation of state model is here the Peng-Robinson US model is better, for example, for pentane, which is heavier in terms of which is heavier than methane. But that was the fundamental problem by that time, that these two parameter cubic equation of state model with only two coefficients A and B was not able to predict good or accurate liquid phase densities. And you can see here these are the vapor phase densities down here, and these are very accurately predicted. They don't have much impact with this problem. Yeah, so we will just look at how this cubic equation of state model can be applied for pure component, and then we will also do a very good exercise on it, which will also give you a better understanding of what a cubic equation of state model is and how the calculations are done, for example, in all these PVT packages for pure compound at least. So if for a single compound, the vapor pressure, we know it's a pressure at the given temperature where we have both saturated liquid and saturated vapor phases that exist at the same time. And the way we can calculate the vapor pressure for a pure compound is that if we plot the pressure versus volume diagram with a cubic equation of state model, it would look like this. This is like a continuous function of pressure versus volume with a cubic equation of state model here, knowing the A and B, and it's a constant temperature. So the way the vapor pressure is calculated. So what we do is we change. So for a given temperature, that's the pressure volume diagram, and we play with the vapor pressure. So we move the vapor pressure up and down, and the pressure value where this area under the curve, so this area and this area under the curve, they become the same. That is called the vapor pressure at that given temperature, because this area here, these are the fugacity. So this is the liquid phase fugacity, and this is the vapor phase fugacity, and these have to be the same, or fugacity is, or we can also say the chemical potential for the thermodynamic equilibrium. So that's the fundamental condition when you are solving the equation of state model. That's the fundamental condition that you need to achieve for a thermodynamically equilibrium solution, that the fugacity of the component in the liquid phase and the vapor phase, they have to be the same when there are two phases. So that's how we come up with the vapor pressure value, that the fugacities of the two phases should be the same at that given pressure. And that's something we will also do in the exercise in the Excel. Yeah, and once we have found out what's the vapor pressure, then generally we just ignore the middle root. So we now know that there are three roots possible. One is this root at this pressure. The other root of the what do we mean by root? Root is the value of the molar volume. We are solving for molar volume or the Z factor. So one is this root, the molar volume. The other is this, and the third one is this. We ignore the middle root, and the minimum value is taken as the molar volume of the liquid phase, or the gas, or the Z factor of the liquid phase, and the higher molar volume is the vapor phase molar volume. So these are just the same slides explaining the similar thing. Okay, I guess we can get started with the exercise that we have on this topic. And the objective of the exercise will be to see how the equation of state models are applied for single component, and to get ourselves familiar with the different parameters in the equation of state model. And for that purpose, we will be using the SRK equation of state model, and just forget about what is written here. So just forget about this here now, and we will see what it means in the coming slides. But what we'll be doing in the exercise is using the SRK equation of state model for a pure compound like water, and calculate the vapor pressure and the equilibrium phase densities. And before we do the exercise, there is something that I want to highlight, and because it's I know it's a kind of a dry topic, and it's the end of the day. So, but the one thing that we had been mentioning before, that for equation of state model development, or for equation of state model calculation, K values are very important. Like that's the fundamental thing in equation of state model calculation. But when we are discussing equation of state models here, we haven't seen K values being used anywhere. Like when we discuss, for example, the SRK EOS Peng-Robinson equation of state, or Redlich-Kwong or van der Waal, we didn't see K values being part of the equation of state model, right? So that's something. It's a little bit confusing, and that's something also that will be more clear when we will have like by the end of this PowerPoint. But the point is that like when we were discussing K values, we said that the K values are only important, or they have any significance when you have mixture. Here we are only talking about pure components or pure compounds, how equation of state models are applied to pure compounds. And when you have only one component or single component, we know that the K value is always 1. There is no discussion on how the K values should look like as a function of pressure, temperature, and composition, because it's the fixed composition, one molecule splitting into 2 phases. So there is no need for the K values. And equation of state models, when you solve the equation of state model itself, they generally give you this the densities, the equilibrium phase densities, and for pure compound, it also gives you the vapor pressure when we solve for this fugacity constraint. And there is no need for the K values to be known. K values are only needed when we apply these equation of state models to the mixtures. And that's something we will see later on in the slides. So that's something I just wanted to mention here. So now we can go to the exercise, and I hope it will be a bit more interesting than going through all these complicated slides of equation of state models. Okay, so in the exercises, it's that's 12, and then we have this H2O Excel-based EOS. So we just open the Excel file here. Yeah, okay, so in this Excel file, we have 2 spreadsheets. We will be just working on the first one. The second one we will use later when we will finish our next topic. So for in this first spreadsheet, we have so what we have here, so that's we are using Sawe and Redlich-Kwong equation of state model. It was built by Curtis actually, and so we will be using water as a pure compound for these calculation, and these are the component properties that we know for water. We know the molecular weight, we know the TC, we need the PC, we have the PC, and we also have the centric factor, and these are just well known for water. And just forget about this S, what is S and why it's a 0 value. So we will not be using this for this particular exercise. And we will come back to that in the next session, what is S actually. So, and then here we have the pressure and temperature. So what we will be doing, we will try to use the SRK equation of state model to calculate the vapor pressure at 100 degrees C, which is the boiling point of the water. And we will see, and we already know that the boiling point at 100 degrees C, since it's the boiling point of the waters, and then the answer should be close to this standard pressure, which is 1.0135 bar. Absolute. These are like these calculations were done in phase comp, which is the PVT package we internally use using the SRK equation of state model. And what what we have found there, that if we use the SRK equational state model with and try to find the vapor pressure at 100 degrees C, it gives us 0.9274 bar absolute. And similarly, you can also do the other way around. You can calculate, instead of calculating the pressure at 100 degrees C, we can calculate the temperature at 1.0135 bar, and it should be close to 100. So that's 102 if we calculate that. And so that's the results on the vapor pressure. So these are the results we should expect to get from this spreadsheet, because these are from PhaseComp or the PVT package. And regarding the densities, the liquid phase density at this vapor pressure with this SRK equational state model, that's 0.7104 gram per cc, and we know water density and the liquid phase density at the boiling point for water, it has to be about 1 gram per cc, so close to 1 gram per cc. So you see that there is a big deviation. So if you can just quickly calculate, for example, the deviation, so it's divided by 1, so that's the same. So 30% off. So yeah, and we have already discussed that the densities from the cubic equation of state models, they are highly underpredicted because of the reasons that we discussed before. And the vapor phase density should be very accurate, so that should be okay. So what we are going to do in the exercise, we are gonna do the same calculation, try to come up with the same answers that are shown here, coming from the PVT package, and try to apply this Redlich-Kwong or SRK equation of state model. So yeah, just to get my life easy, what I will just do is I will just go into the phase behavior monograph, and then just copy the equation so that I have them in front of me while I'm doing the calculation. So where's chapter? So that should be in chapter 4. Yeah. So we know that the Suave SRK equation of state and Redlich-Kwong equation of state are essentially the same, and it's only the alpha correction that's different. So we just take the snapshot of the Redlich-Kwong equation of state. I hope I will be able to do that. Please, please, please. Oh. Just copy this to the Excel file here. So just to have it in front of me. And then we know that this is the correction term that we want to have in the SRK. Again, oh, please, please, please. Okay, just leave it. We will just use it from the PDF. Okay, so the first thing, the value of R, and for the unit system we have here, that's mainly SI. So the value of R we can use is 8.3134. So that's the value of R we can use. The omega A value that we can see here, where is that? Yeah, omega A 0.42748. That's our omega A. 0.42748. 0.42748. So that's this number here. Just to make sure I cannot use pen. Oh no. Yeah, so that's this this guy here, and then we have omega b, which is 0.08664, 0.08664. The value of m, so we know that the m is a function of the centric factor, and that equation is here actually in the monograph, 4.17. That's the m value from the SRK equation of state, so 0.480. Just write it here, equal to 0.480 plus 1.574 times the centric factor, which is here for water, plus, or sorry, minus 0.176 times the centric factor square. Yeah, so that's good. So that's the value of m, and then we can calculate the alpha value from the Suave, which is this number here. E is equal to 1 plus m, that's this number here, times 1 minus square root of the reduced temperature. So the reduced temperature is, we haven't calculated here, we can calculate here that number times the square. Sorry, that is supposed to be a square. And the reduced temperature should be T over Tc. That's the absolute temperature divided by Tc. So 1.539. And we can also, just for the comparison, we can compare it with the Radley-Cohen alpha correction term, and you see that they are quite different. And here, this is just coming from the square root of the reduced temperature, which was constant for all the compounds. Then we have A. So A is this guy here, equation 4.12. A, so omega A times the R square times the critical temperature in Kelvin. R square T square or PC. PC is in bars. That's this number here. Times the alpha correction. This number here. And then we have B, which is omega B times R times Tc. So R times critical temperature times over PC, or over the critical pressure. So that's the B value. There is something. So omega B, the B value is where is B? So omega B times R times the critical temperature divided by the critical pressure. Okay, so that's the B. Where is that? Okay, the reduced pressure is P over PC. Yes, that's not right. And then we have the value of A, which is omega A times the reduced pressure. The reduced pressure is this number here, divided by the reduced temperature times the alpha correction term. P over R. Ah, so that's actually correct. That Elena, yeah, that's Elena. That's right. So this has to be 83.134 for the unit system that we are working on. 143. Yeah. Thanks. Yeah. So now we are calculating the value of A. That's simply the value of A here times the pressure, and the pressure is this number here, bar, and then divided by the RT square, so R times the temperature and the whole square. And then we have B, which is B times RT, B times pressure over RT. R times T Okay. Now we go to, so we calculate these coefficients here. So the coefficient for this cubic term, that's 1. So that's 1 here, and here it's for the square term it's -1. The A this coefficient here, so that's A minus B. A minus B minus B square. And then the next and the last one is A times B. A times B. Okay. So with these coefficients here, that's the cubic equation of state, and we get these roots. So this is just that's just the code that is taken from this VBA code lifted from this website here, just to solve the cubic equation. So it gives us 3 roots. So there are 3 real roots, and what we are gonna take is we take the root that's the minimum root for the. So we are gonna take this Z1 as the liquid phase root, and then so we discard the middle root, take this one as one root, that's the liquid phase, and then the gas phase is this number here, the vapor phase. And then what we will do, we will try to minimize, because now here you see that there with these we have taken these roots, and with these roots we have calculated the fugacities, the liquid phase and the vapor phase fugacity, and this is the fugacity expression for the SRK, or the quantification of state model. So this is we have calculated, so this is being calculated here, the liquid phase and the vapor phase fugacity, using the liquid phase and the vapor phase root in this equation. And then this is just the difference, or the error between the 2 values, which we try to minimize using the solver, and then try to change the pressure, see which pressure do we get to get the answer. So that will be the vapor pressure when the 2 fugacities will be will be the same. Try to change this number here by minimizing the number here, that's the error between the 2 fugacities, and then just try to solve it. So we see that it's minimized to exponent -24, which is good, and the value we get using the solver is 19274, which is essentially the same as 19274 from FaceCom at 100 degrees C. So that's the vapor pressure calculated by SRK, equation of state model, at 100 degrees C for water. And now if you want to calculate the densities, so density now is very simple. We can use the PV equals to NZRT. We know the roots, the Z factors for the liquid and the vapor phase. So we can just take the Z factor times pressure. The pressure sorry, it's the pressure times the molecular weight. Pressure times the molecular weight, which is here, divided by the Z factor calculated, times the R value times the P value. So this is the in gram per cc, the liquid density, and the same can be done for, I will just fix the formulas and just drag it down for the vapor phase. And if we just compare these two numbers with the numbers we have gotten from PhaseCon, 71024, 71026, and 0.00054, 0.00054. So yeah, so that's how in the equation of state model can be applied to a pure component to do the phase behavior calculation, calculating the vapor pressure and also calculating the densities at vapor pressure by maintaining this viscosity constraint. So I think that this is so any, I don't know if there are any questions on the exercise. Curtis, you want to say something?
Yeah, I mean, this shows the mechanics of how an equation of state can be used for a pure compound, or as you'll see later, it's the same exact equations if you have a mixture, and that mixture is single phase. You just calculate an average A, an average B, kind of a molar weighted average. And once you get the average A and average B for the phase, you can calculate its density as well. You can't do the equilibrium calculations in such a simple way, but just the volumetric part, you can do that way. Just an anecdote, kind of an interesting thing about water is that you can you get the vapor pressure here exactly at this temperature, and you can introduce the volume shift, which maybe you want to do on your own, or we do it later, so that the liquid density is closer to 1 grams per cc, what it should be. Boiling water has a density of close to 1 gram per cc, right? And what it is now is 0.7.
Yeah.
And so it's 29% off. Okay, so if you go look up in your steam tables, density of boiling water, you know, it should be, I don't know exactly what it is, but around 1 gram per cc. It's close to 30% off. And with that volume shift factor up there, the S, you can correct that to be whatever that value should be, 1 or close to 1. Now, even if you do that, the cubic equation of state, if you ask it to calculate the compressibility of water, for example, at 1 atmosphere and 60 Fahrenheit, okay, not at the boiling point, but just tap water coming out of the faucet. That tap water should have a compressibility of, depending on the units, somewhere around 3 times 10 to the minus 6 inverse PSI. The cubic equation, even though it's getting the water density exactly right, let's say 1 gram per cc at 1 atmosphere and 60 Fahrenheit, the compressibility it'll calculate won't be 3 10 to the minus 6. It'll be around 1.3, I think, 10 to the minus 6, which is more than a factor of 2 too low. So the compressibility of water, every petroleum engineer knows, is important, right, in terms of getting water influx correct, well test analysis correct. Getting the water compressibility is a very important property. And you basically can't get it from this cubic equation of state the way it's used now, where we tie the A and B to the critical properties. Now, the critical properties are not of interest, right? 647 K is very, very, very high temperature. We're never going to be close to that. But finding the A and B in this manner, according to
Van der Waals.
Yeah, the Van der Waals actually gives 3 ways to do it, but using the PCTC, that's status quo, will give you an equation of state for water. Get the vapor pressure right, can get the density right, the tap water or the boiling water, can get all that stuff right. The steam density right will be very close, but it can't give you the compressibility by better than a factor of 2 or worse than a factor of 2. That's something that nobody really talks about, but it's just a fundamental failure of the cubic equation of state. It doesn't have the correct pressure volume temperature relationship everywhere. So it's just kind of an interesting fact. Nobody is computing, not PVT7, nobody's computing water compressibility for you to put in your reservoir simulator or well testing program based on the cubic equation of state, despite the fact that you can get it to predict all these other important water properties accurately. So it's just a kind of a footnote.
And just one comment, Coris. Correct me if I'm wrong. So when you're saying that the cubic equation of state model is not predicting the compressibility, right? It means that the cubic equation of state model is not predicting the variation of density with respect to pressure, right? So you can use the volume shift to match one density point exactly, but you may not get this function of density as a function of pressure. Exactly.
That's right. You can get it right at one pressure, but then if you just move over in pressure and want to know the density there, it's going to be way off.
Yep.
It's basically the pressure derivative of density is not being calculated accurately at all.
Yeah. Yeah. Think. Yeah, so this volume shift, what is volume shift? And we will go through this tomorrow and then just do the same exercise in introducing the volume shift. So it will be almost identical, except a very small change that we will see tomorrow when we'll do the same exercise. And yes, let's see how much we have to cover on volume shifts. Yeah, so I think we can, and there is a, maybe we can finish the session today now, I guess, because the next topic, if we will start this next topic on the volume shift, it may take some time and we may go over time, which is may not be okay for some of the people here. So, Matthias, do you think it's okay?
Yeah, we have 15 minutes. So is there any questions in general about some of this? I think from when we've done this course sometimes now, and this is the part that probably many of us might seem as being the most far-fetched from what we do on day-to-day basis. But it's very, very nice if you work on these things, at least seen this stuff at least once, and because that will really help you when we get to the topics tomorrow, which is actually purely on the practical aspects of creating and tuning an equation state model. Hopefully by the end of the week on Friday, we're able to connect the dots going backward a little bit to see the big picture and how this affects the things that we talk more about in a day-to-day setting. Curtis?
Yeah, no, I mean, I think it's people are tired and it's kind of heavy stuff for us normal engineers. So I mean, it's if there's no questions, maybe we'll just ask if there's any questions before stopping. I'll make a couple of comments if there are no questions. I'd rather have the questions come, and if there's any out there regarding the cubic equations of state. I mean, one of them should be, why would you use the Payne-Robinson instead of the SRK?
Yeah. Which US is more preferred? Yeah, that's a more general question we usually get from
maybe does anybody have any thoughts about that, or are there any like company policies out there for people who use software that you're supposed to use the SRK or the Payne Robinson, or it's up to you? Any thoughts or comments to that?
I only came across Payne Robinson my entire career, so it's yeah, but it's just because I'm a follower, so not because I ask the question.
Right.
Okay.
Right.
Well, for me, it's more than. Sometimes it seems that SRK fits better, and sometimes Payne Robinson fits better.
Yeah, that's very likely everyone's experience if they use both enough. Because the SRK came when it came earlier than the Payne Robinson, even though it was only a few years earlier, the process industry was, and refining and mainly process industry, really took it to heart and started using it very actively as soon as it came out, because it did such a great job in predicting the accurate processing of gases in particular to extract out liquids and liquid products, and altogether optimizing separator conditions, designing large process facilities like the Ecofisk. And what was available was the SRK and commercial software, the early commercial software. So that became the hat all processing chemical engineers wore up until Payne and Robinson in 76, but then they had to fix the equation in 77, 78 with this quadratic term on the M. And so if you asked anybody in 1978 using equations of state in the process industry, they would say, well, there's no reason to change to the Payne Robinson. They were all on board with the SRK. That continued through the 80s and probably into the 90s. Then Payne Robinson, they came along and they gave an equation of state that predicted better densities of oils, but still off by 10 to 20%. Instead of being off 20 to 40%, the SRK would predict stock tank oil densities maybe 20, 30% wrong. Tank oil densities with the Payne Robinson were off maybe 10 to 15 to 20%. It was better, but it was far from being good enough. And so why do if you ask all petroleum engineers today, or let's say in 1980 and 90 when it really started being used, petroleum engineers, what equation of state do you prefer? They would have said the Payne Robinson equation of state. And you actually had this kind of war going on between process engineers and reservoir engineers, because reservoir engineers started using compositional reservoir simulation with the EOS starting in 1980. They didn't use it very much, but the first commercial EOS reservoir simulator by Keith Coates came in 1980 publication. So in the 1980s, you started doing more and more compositional reservoir simulation, but the EOS being used by the reservoir engineers was boohooed by the process engineers. Didn't have enough components, didn't use the right equation of state. They wanted to have an SRK with more components. So it was like the two groups didn't talk to each other. So the question is, why did the petroleum engineers start using Payne Robinson instead of the SRK? Well, the reason for that is Robinson came out of the University of Michigan. That's where Katz was, okay? And the first paper on cubic equations of state in the petroleum engineering literature was the Katz and Fears of Body paper in 1978. And there was actually another paper, I think in 77 by Katz and Bergman. Bergman was one of the late PhD students of Katz, University of Michigan. And out of this camaraderie, I suppose, they published Katz and Pirzabatti on the Peng-Robinson equation of state. So it was an arbitrary choice in a sense, in terms of, what school do you root for when they're playing football. It was more or less like that. There was no definitive paper that said in 1983 the Peng-Robinson is always better than the SRK. Okay. Certainly not 1983, because in I think it was 81, the volume shift came in, which we'll talk about tomorrow, I guess, by Penalou. I think it was 81. And at that point, they made the accuracy of gas and oil densities between the SRK and the Peng-Robinson essentially identical, and within 2-3%. So there was no reason, to choose SRK versus Peng-Robinson. So really, the petroleum engineering industry took the Peng-Robinson simply because the Katz-Pirzabatti paper was the first paper they saw. Keith Coates also, who did the 1980 paper on reservoir simulation, used the Peng-Robinson, and he was also a University of Michigan PhD student. So it was a little bit alma mater, if you will, decision for the Peng-Robinson. Whereas for the SRK, it was the first thing available in commercial software in the early 1970s. So that's kind of the background for the two equations of state. Now today, if you go to the process engineering or the chemical engineers doing process engineering with HYSYS, and you ask them, they'll probably say, I don't really care. And one of the reasons for that is because the equation of state work being done for reservoir engineering applications, and probably the vast majority of that being done with PVT SIM the last 30 years, was accepted by the process industry. In other words, the process engineers didn't have to develop their own equations of state any longer. The PVT SIM usually gave 22 components, enough detail. Of course, it recommended and only had the SRK in the first 10 years. But then when the Peng-Robinson appeared, likewise for HYSYS, not that HYSYS didn't get the Peng-Robinson until 15 years ago. So, but once the last 15 years, coming out of PVT SIM or HYSYS, the characterization could be randomly Peng-Robinson or SRK, it didn't really matter. So it basically that argument for one being better or preferred over the other died out about 10 years ago. I don't know if there's any questions, but that's kind of the status today. There's never been a singular paper that says this is why you should use the SRK or this is why you should use Peng-Robinson for petroleum systems.
Okay, yeah, there is a question.
Hi, yes. There are some scenarios where we have a transition, right? Transition to dense phase. So in that case, which one is the recommended, or which one is better compared to? I think both are equally, both SRK and Peng-Robinson will have equal issues with respect to handling dense phase transition, right? So in that case, what would be the advice?
For water?
No, not for water, for the hydrocarbon mixture.
Yeah. And the question, could you just repeat it one more time? It was a little bit low.
No. What I was asking is, for example, in a topsides process simulation with using HYSYS, whether it is SRK or Peng-Robinson, we have found that both of these struggle when there is a transition to dense phase.
A transition to dense phase.
Yeah. So in that case, HYSYS has an option while defining the fluid package to force it either to the liquid phase or to the gas phase by dense phase tuning factor.
Okay, what would you call a dense phase? Is this
above the Craig-Hendon bar? Say.
Okay, yeah.
So in that case, is there any recommendation on the
No.
effectiveness of SRK or
No.
Peng Robinson,
No.
or which one is better?
No, not at all. I don't think that what I would just call single phase, you're calling the dense phase, basically at high enough pressure, it's single phase. Single phase, high pressure gas or oil won't be predicted better by the SRK or the Peng Robinson consistently. I don't believe anyone's shown that, and I wouldn't prefer one over the other. When you get to high enough pressures like 7, 8, 900,000 bar, neither of the equations are going to give you compressibilities. Well, even at 600 bar, the compressibility of single phase gas or single phase liquid will not be right. For the same reason it's not right for water. The cubic equation just doesn't have the pressure volume dependency. It's cubic and volume. It needs to be different than cubic and volume to be right, to get the compressibilities right. So any single phase high pressure gas or liquid would suffer from, you might get the right density at initial pressure, but you won't get the right compressibility at the initial pressure.
So in those type of scenarios, then what is the go-by method to ensure that what the simulation results are given are right?
Using a compositional model with an equation of state. Was the question how to make sure?
No. The question was actually, yeah, I understood that both will have issues because the predicting the compressibility will not be right. But in this case, what would be the go-by method? What is the recommended method to ensure the simulation results?
Yeah, so the equation of state will never get the compressibility of the high pressure gas or oil right. That means that your recoveries are going to be wrong. The material balance it calculates in your simulator, every grid cell, it'll be wrong, okay? And maybe significantly wrong. You could try to use a black oil model, but the problem with that is it's generated from the equation of state now. So the black oil tables would have the same poor compressibilities at high pressures because they're generated from the equation of state. So you have a problem with high pressure gas and oil reservoirs in reservoir simulation. There's kind of two approaches to dealing with that. The one is to use a more sophisticated, like a BWR type equation of state to get the compressibilities right, and then generate the black hole tables with that equation of state. But there's almost nobody using BWR type equations of state for these mixtures, petroleum mixtures. The other would be to use laboratory data, CCE data in the single phase region up to initial pressure, and to create synthetically or manually the BO or the BG pressure dependence that honors the laboratory measurements of compressibility, which would be correct. So it would be a manually created black oil table. If you have to use compositional equation of state modeling and want to get that right, the compressibility of the system and the recovery of the system from high pressure to, let's say, down to saturation pressure, the only way to do that is to correct the total system compressibility, meaning rock, water, and hydrocarbon. Hydrocarbon is going to be wrong. So what you have to do is you have to artificially change the water and or rock compressibility to give the correct total compressibility so that you get out the right amount of fluid as you deplete the pressure. So that's been done in a number of cases in HTHP reservoirs. You have to do this, again, it's a manual exercise to get those water and or rock compressibilities to change as a function of pressure such that the total system compressibility is changing correctly. Those are your three options.
Okay, thank you.
Most people just ignore it and don't know that it's wrong.
Okay, fine. Oh, this is one thing. There is another question. Actually, apart from these SRK and Peng-Robinson models, right? Nowadays, I think there is one more thing which is called the Cubic Plus Association (CPA), which is being introduced by a software like Multiflash. I think KBC. I think they have made that CPA as the default model. So, could you also elaborate on the application and usage of the CPA?
Is it being used in a reservoir simulator, you said?
Yeah, even Multiflash with the one which is by KBC, no? Now with the
Yeah, the Multiflash, but that's not a reservoir simulator. That's more for process simulation.
So they say that CPA is advantageous when handling systems with water, and when we encounter hydrates and we use MEGs to determine the partitioning of hydrate inhibitor between the phases.
Yeah, no, they will help you get partitioning of components into the aqueous phase and from water into the non-aqueous phase correctly and more accurately, but those are not available in reservoir simulators. I think you have some of that in PVT Sim, and you have some of that in the KBC Multiflash software, but not reservoir simulation. I still haven't seen whether the CPA gets the compressibilities correct. I don't think it does. So for water.
Okay.
Yeah.
So what I understand is, except that partitioning, it doesn't have any other specific advantage. So in that case, is it if polar components are present, is it better to cross-check with CPA only for that specific aspect and do the other simulation in with SRK Peng-Robinson, or how it will work?
I think there's been a number of publications, and one of which we did back in I think it was the late 80s. Shows that the cubic equation of state can be used very accurately to get component partitioning for aqueous and non-aqueous phases in petroleum applications. You have to use a different mixing rule, but the cubic equation can be used to get quite accurate mutual solubilities. What the CPA brings is probably on these systems like MEG, more chemical. Yeah, the water chemistry becomes more complicated, and that's probably where you gain with the CPI, as I understand it. But I don't think we're ever going to see that being used in reservoir simulation, to be honest. But who knows?
Okay, thank you.
Sure.
And what you see on the screen is the software within PVT, and I think everybody has access to that. If you just go to courses.witson.com and log in with your emails and the password. The fluid, if I just go to the fluid model, so here we see the equation of state model that we are going to develop today. But the reason why I'm showing it is because there are already things that we are familiar with now, and that's just good to show now that what we have gone through with this with the equation of state model. So if you look at the screen on the top, you see that the fluid model summary. So that's just the name of the equation of state model we will be developing. So that's an SRK EOS, and that's just the error and the EOS model, when SRK EOS model was published actually. And then we have the total number of components here, 31. So the EOS model will have the heaviest fraction C26 plus, which is the heaviest fraction in the lab reported data actually. Viscosity model, that's something we will discuss today also, so let's just forget about that. Field-wide gamma models, that's something we have already discussed, so you must be familiar with now what is the shape factor alpha, what is the bound, and then this is the gamma model for the C7 plus distribution. How we found out that the shape factor is 0.783 and the bound is 96. That's something also we will go through today during the exercise. If you look at the equation of state model, so Matthias, he mentioned first day that the EOS model have two tables. So one is the component properties, so that's one table. The other is, if you scroll down, that's the binary interaction parameters. And we haven't seen binary interaction parameters until now because we were only discussing the equation of state models for pure components. So we will come back to this binary interaction parameter term now when we will discuss how the same EOS models are applied to the mixtures. But the things that we are already familiar with now is the components. Of course, if you have a multi-component system, we have multiple components here. The molecular weight, and the TC, the critical temperature, the critical pressure, and the eccentric factor. So this is critical Z factor, and this is volume shift. So volume shift is the next thing on the list. Eccentric factor, we already know now that, for example, if you want to use Peng-Robinson EOS model or SRK, we at least need molecular weight, TC, PC, and eccentric factor if you want to use that equation of state model for a pure component. So these are the terms we are already familiar with: molecular weight, TC, PC, and eccentric factor. This A and B, these are just omega A and omega B, which are constants for all the components, which we have already gone through also. And then these L and Ws, these are the lower molecular weights. And we have also gone through this in connection with the field-wide gamma distribution model, where we said that if you have the three parameters, the shape factor, the bound, and the average molecular weight, which is not shown here because that's, it's a sample property. So it's different from one sample to another. We have two samples in this course, oil sample and a gas condensate sample, and both have very different C7 plus molecular weight. So here we are only showing what are the common properties for all the samples. So that's the shape factor and the bound, and the lower molecular weights, it's also constant for all the samples, and that's something we know that these are used to discretize the continuous model to get the individual component amounts and the molecular weights. So now what is missing in this table that we are not familiar with is the volume shift. That's something we will discuss now. The ZC or critical ZC widths. These are used for the viscosity model, and that's our LBC. So that's something we will also discuss today, hopefully. And the boiling points. So these boiling points are not part of the equation of state model. They are only shown here because these are used to characterize our heavy ends, and we will see. And when we will discuss in detail the C7 plus characterization workflow, how and why we use the boiling points to get these other properties which are required in the EOS, that's TC, PC, and eccentric factor. And again, the second table, we will also go through that binary interaction parameters. So now we can start our new session. Are there any questions related to the session we had before, or like yesterday? Yeah. Okay. So I think we can start the third parameter in the EOS model. So we know that the equation of state models, either SRK, Peng-Robinson, they have two parameters. That's the small a and small b that actually came from the van der Waals equation, the two parameter cubic equation of state model. And we already, so this is just the whole summary of what we discussed yesterday, that the main issue with the 2-parameter cubic equation of state model, and I'm emphasizing that's just the 2-parameter A and B, so that's your small a and the small b for each component. That 2-component equation of state model, a 2-parameter cubic equation of state model, it has this limitation on the liquid phase density. So the liquid phase density, we did the exercise yesterday. Water phase density, it was calculated about 0.7, and we know that the density should be 1 gram per cc, close to 1 gram per cc, and it was giving us about 30% error. So these 2-parameter cubic equation of state model doesn't predict the liquid phase densities with accuracy, and that has been a great issue. That had been a great issue with the cubic equation of state model until this 3rd parameter in the cubic equation of state model was introduced. And there were different attempts to improve the capability of the cubic equation of state model to predict accurate liquid phase densities. But the Penalou, Curtis, again, he can tell you about the interesting stories about these people. But the French people came up with an excellent idea of how to introduce this 3rd parameter in the cubic equation of state model, and their idea was so excellent because the way they introduced this 3rd parameter in the cubic equation of state model, it didn't change any capability of the equation of state model to predict accurately the vapor pressure curves or the vapor liquid equilibrium predictions of the cubic equation of state model. So because at that time people have already programmed, for example, SRK, Peng-Robinson equation of state models in the for example the process simulators or mainly the process simulators, and they didn't when they introduced this concept, and Curtis, he will again tell you a very interesting story about Keith Coast when he called him mid of night. Maybe Curtis, you can just briefly go through the history if you are okay with that.
Yeah, so basically when people started, as I mentioned, 1978, Katz and Firzabadi, Coates, 1980, people started using the cubic equation of state in petroleum engineering software. One of the big immediate problems was this inaccuracy in the liquid density, oil densities, which can be very important for gravity, processes involving gravity. Obviously, pipe flow in the reservoir, high permeability, gravity segregation, gravity stable gas injection, initialization of reservoirs where capillary gravity is assumed to determine the initial water saturation. So there's a lot of reasons why you want the gas and oil densities accurate within a few percent and not what the SRK and Peng-Robinson was providing. So before this Penalou, the accuracy was for SRK 10 to 40% in error, basically densities that were too low. And Peng-Robinson was maybe better, 5 to 25%, again, under predicting the oil densities. And, this was just really unacceptable. So a lot of people were working on trying to fix the 2-parameter equation of state, myself included. But Penalou and his co-authors, they came up with what solutions being used today, and very successfully, and it was a very, very clever idea. So the way around the problem prior to the implementation of the Penalou volume shift, basically people had different approaches to fixing, quote unquote, the 2-parameter equation of state. The most common ExxonMobil and Amoco and now BP used was to determine correction terms to the A and B beyond the default SRK and Peng-Robinson A and B value for each component. And those correction terms were highly nonlinear. They were using spline tables. They were difficult to reproduce. They basically introduced a lot of complexity in order to get both accurate gas and in reality, with these correction tables, the pure component critical properties were not being honored. TC and PC, acentric factor. So there was that was one approach, and then Keith Coates presented a paper in the early 1980s where he introduced the idea of correcting the A and B of all the C7 plus components as a single parameter, single correction term. And another two correction terms, which was the A and B of methane. And then his fifth parameter was the binary interaction parameter between methane and C7 plus. So he had basically a 5-parameter type tuning process, and he showed for almost 15 complex reservoir fluid systems that he could predict, or he could match very complicated phase behavior of gas condensates, oils, and so forth with basically these 5 correction terms. But he changed the A and B of methane, for example, by a factor typically from plus or minus 20 to 30%. And a similar correction for the C7 plus components. And a lot of people were very uncomfortable with doing it that way, but it did get the job done. Like I said, he has a classic paper where he shows an example of using this approach for, I think it was 13 or 15 reservoir fluids with complete PVT data sets given, gas injection, near critical, basically the A to Z of PVT data. And in I guess it was around 1990, 91, 92, we were at a conference together in Austria, and actually our bedrooms in the hotel there were next to each other, and we spent quite a bit of time that week talking. He had just left his company, the first software company in petroleum engineering, Scientific Software Intercop, and he had just left to go on his own, and he was going to start writing from scratch reservoir simulators, compositional, which is black oil, which is now called sensor. And to do that, the first thing he had to do was to program up the equation of state and the PVT, a new PVT package. So during that week, I gave him, I mentioned to him, and I think in my lecture there, I talked about this volume shift as being a kind of a very important step forward for the use of cubic equations of state in petroleum engineering. And so we left, and I guess it was maybe 2-3 months later. He was living in Florida, and I got a phone call in the middle of the night, and he says, Curtis, this volume shift. When I put it in and ran all of these 15 cases in my original paper and used the C7 plus characterization methods that you were recommending with the volume shift and the specific gravity molecular weight, blah blah blah. Basically using these methods that were available, but he hadn't implemented earlier. He said the predictions of the majority of these PVT data were as good or better than what he had originally tuned. And he says with no corrections to the omega A and B of methane at all, and very, very small corrections to the A and B of the heavy components. And he was just shocked. And he rambled on for about 10 minutes without interruption. And when he finished, he says, well, thanks, Curtis, and he hung up the phone. And it was that dramatic, the improvement made by this volume shift. If I can just share the screen real quick, I'm just going to make one. I've made a couple of comments on one slide here. Your starting slide, Bilal. I know I'm burning up time here, but I just thought I'd introduce this. Can y'all see the screen now? because I do consider this such an important. So this was kind of the state in 1982. So basically, we had this. We had these. Can you all see this cursor?
Yeah.
Here. Yeah. So basically, we had these percent errors in liquid density of any stock tank oil, reservoir oil. And in fact, some of these errors on the low end, maybe 5 to 10%, depending which equation of state you're using, would apply to high pressure gases as well, gas condensates. So this was kind of the state. And I've got a footnote here which says that in the pre-1982, and for some of the software, like I was mentioning Keith Coates, and into the mid-1990s, most of the used EOS-based software, including HISYS and PVT Sim, did not have the volume shift included. And as a result, we're getting these kind of densities. So they had to have, actually, that's not correct. PVT Sim had the volume shift in there. That's not, I'll take that away. That would be incorrect. It was the Peng Robinson that they didn't implement until quite late. So they only had the SRK, but they did have the volume shift with the SRK. So so what they were getting gas densities, okay. So the software HISYS and in particular as the main surface process simulator, the gas densities were generally okay certainly at process conditions within a couple of percent. So they used the cubic equation of state for gas densities, but for the oil densities, they used a non-cubic correlation. It was by Hankinson. I can't remember the name of it. The default HISYS oil density correlation. Does anybody remember the name of that? The original publication was Hankinson at Phillips, but it doesn't really matter. So they did, huh?
Costalled or?
Costalled, yeah, something like that. Costalled, I think. And with that non-cubic equation of state, you got very accurate oil densities, which was great. But at process conditions, you never really were operating near a critical point, so you didn't need the consistency of having near the critical point the gas density and the oil density approaching each other, which you wouldn't get using this approach. In reservoir simulation, where they were looking at developed miscibility and miscible processes, and you had near critical phenomena, there you needed this consistency of the gas density and oil density approaching each other and becoming equal at a critical point. And that you would get with this Pendeleu volume translation method. And with this simple correction that Bilal's going to explain, basically this brought down not only the liquid densities, but the gas densities, even at high pressure, brought these down to plus minus 1, and at worst, you can always get it within usually 2%, between 1 and 3%. So we're in a range of accuracy that is almost the range of experimental accuracy. So with this, you can now use both in reservoir modeling tools, pipe flow tools, where you're using the equation of state. You need accurate densities because of the gravitational effects, and in surface processing as well. You can use the single cubic equation of state with the volume translation to get the type of accuracy is required for engineering calculations. So that's kind of the backdrop on this volume shift, and it was something a lot of people missed because it was published in Fluid Phase Equilibria, European journal, and petroleum engineers basically didn't read it. A lot of us missed it for a long time, and it really was an important advance in equations of state. So I think that's all I wanted to kind of give that summary. Any questions, or can take that? Probably questions after you explain it. So let me just turn it back to you, or you can just take over the control.
Yeah.
There we go.
Yeah. So very good, Curtis. I think everybody should have enjoyed this historical part of this volume shift. Yeah. So what I'm gonna discuss here, is Curtis has mentioned like why and how like what is actually the method. That's something I'm gonna discuss now, and why it is why it was so elegant and simple. That's something you will see in the next slide. So what their method, what they propose for this volume shift or for correcting the densities, and they said that you can calculate all your molar volumes with your 2-parameter cubic equation of state model at any given temperature and pressure. So meaning that you just do your EOS calculations the same way as we were doing before, and then once you finish doing your cubic equation of state model calculation, you just correct the molar volume by simple this term here. So this is this is now your corrected molar volume. Corrected molar volume coming from the cubic correct molar volume, and this is the molar volume or the incorrected molar volume from the 2-parameter cubic EOS. So just do the same calculation with the 2-parameter cubic EOS, and at the end, once we finish the calculation, just subtract this constant term here from the 2-parameter cubic molar volume and get the corrected molar volume. And this C term, this C number here, that's the volume translation for a given component. So it's different for each component, and yeah, and that's something we will also see in the next exercise, like the exercise that we did with H2O yesterday. It was without the volume shift, and we had the very bad densities. And now we will do the same exercise with the volume shift and see how this equation can be used to correct for the density. And with this correction, because you see that this is a very simple correction. You're just doing the correction on the molar volume after doing your EOS calculation. And the best thing about this correction, it was very simple, and it didn't affect any phase behavior or vapor liquid equilibrium calculation. So the vapor pressure of your the vapor pressure calculation, for example, for pure component, or when we will go into the multi-component system, the K values and the saturation pressure, all these K value dependent phase behavior calculation, they remain unchanged. And you will see kind of reason next on the next slide. But before we jump to the next slide, just a comment here that this value of C, the value of C can be a positive value or it can be a negative value, and again, that's different from one component to another, and that's actually the third parameter in the cubic equation of state model. So that's why we were calling this a 2-parameter EOS, because it had 2 parameters that were A and B. And now this is your third parameter, C, which is the volume translation, which is used for the improvement on the liquid phase density. And it doesn't affect any phase behavior type or vapor liquid equilibrium type calculation with this Panelu method.
Just a historical note that's still important to know.
Yeah.
When you take your equation of state from whatever software you're using, and the process engineers are using HYSYS and taking your equation of state, 20 years after this method was introduced, finally HYSYS got around to implementing that as an option. And when they did it, they used the wrong sign.
Yeah.
They took the 2-parameter volume and added the C term. So what you have to do is you have to take the C values generated in your PVT sim, phase comp, PVTP, whatever it is, All other software values of C, when you import it to HYSYS, you have to give the negative of that C value, which is a commentary on companies that become monopolies. And literally, HYSYS was a monopoly that was broken by the U.S. government about 20 years ago because it had a monopoly on the process industry, basically phase behavior calculations. And so that's why you now have the Unisim software. I think it's Honeywell or somebody. They had to basically give the existing code at that time of the monopoly decision. They had to give their code to some other industrial company for them to develop it independently and create a competitive environment. So anyway, when you when you get too much control, you can do what you like. But they had this still implemented incorrectly. So
yeah, so that's what Curtis is saying, that in the HYSYS, this molar volume term here, the corrected molar volume is calculated with this plus sign instead of this negative sign here. Very good. So this is just a slide showing you why this correction that was proposed by Panelu on the volume in terms of volume shift, it doesn't affect the phase behavior liquid calculation, like the phase vapor liquid equilibrium type calculation. So if we make, for example, pressure volume diagram for a pure component with a 2-parameter cubic equation of state model, we know that the function looks like this, and then the vapor at the vapor pressure, we know that the liquid phase density is this point, and the vapor phase density is at this point, and we disregard this middle root, and then these are the fugacities that should be equal. And we know that this liquid phase molar volume or vapor phase molar volume, these are not correct with the 2-parameter equation of state model, and these have to be corrected with this Panelu correction. So when you do this correction, that's something we see on the right. So now this blue curve is now with the gray, light gray color. That's something you see at the back. And then this green is after the volume translation. And you can see why it's called volume translation, because it's shifting the entire curve either left or to the right. And here it's shifting it to the left, considering that the C is positive here. So now the new volume translation, new molar volume or the corrected molar volume with this Panelu method, that's this liquid phase molar volume and the vapor phase molar volume. And that's just simply getting this old or the wrong molar volume minus the C. So you're shifting the entire curve to the left. And what you can prove that these fugacities, then because now since we have moved the entire function, so the area under the curve, so this liquid phase fugacity here and the vapor phase fugacity here, the values will change. But you can prove it mathematically that even though the fugacity of each phase will change, but this equal fugacity constraint, it will still remain valid. So the new fugacities will also be the same between the two vapor phases, just like the old fugacities which were here. So that's why the vapor pressure calculation didn't change because of this volume translation. And that's why this method was very elegant, and it didn't require a lot of effort in implementing it into the PVT packages that those were there, and also these simulators that were there, which had already programmed SRK 2-parameter EOS or Penn-Robinson 2-parameter EOS. Yeah. So now just some more information about the volume shift. So the volume shift, this is for each component, that's the value of C That's the volume translation, and we discussed this before. It has the same unit as the molar volume, lb mole, because this is directly being separated from the molar volume. And this B term, this also has the same unit, lb mole. So generally in the PVT packages, the form of the volume shift that is generally used, that's the ratio of the value of C versus B, and that's what we call S, and that's something we will use today in the exercise. And the advantage of using the value of S instead of C is that you don't have to care about what unit system you should use for the value of C, because then it will automatically, because if this is just a dimensionless volume shift, and if you provide these values, it will automatically calculate the value of C based on what unit system you have used for the B. So that's just a quick advantage of S. I don't know, Curtis, if PVT is same, it has dimensionless volume shift, or it still has this this C term here. I don't remember actually.
I think you have to input with the units, to be honest.
Yeah.
I think when it outputs to like Eclipse 300 format, things like that, some of the output formats, it will calculate SI for you. But I think if you input the volume shift, you have to input it with units.
Yeah.
C.
Okay. Yeah. Okay, so now the question is, how do you get the value of C? We know that the value of A and B, those are, so A is the function of PC and PC. Also, we have the same goes for B, for example, that comes from this critical criteria of van der Waals equation of state. But so now the question is, how do you get the value of C for each component? So Panalu, when they mentioned this method, they also suggested that the value of C can be estimated by matching the saturated liquid density at the reduced temperature of 0.7 for each component. And so that's one way. So you can exactly match the density at a certain temperature or pressure of your component. So they suggested that you can do this, calculate the value of C for each component by matching this density, and then there are this is another correlation. This is a correlation that's in the monograph, which gives the value of S, the dimensionless volume shift, as a function of molecular weight, and then there are two constants which depends on what kind of component it is. The approach that I think now is used widely, and it's a simple approach to get this volume shift parameter. And that's to match the known surface density of each component. So for C7 plus fractions, for example, we know that those components exist as liquid phase at ambient condition. And like for example, when you do, for example, TBP distillation, you can measure the specific gravities of those components easily. And we know that specific gravity of each component, it can vary from one field to another. So if you have that data, then you can easily match those densities with the volume shift. So you can tune your volume shift in the equation of state model to get exact densities at those conditions, the surface condition. And if you don't have any data, then there are correlations available. For example, we have Watson characterization factor, and then there are other correlations given in chapter 5 of the monograph, and we will use one of them in the exercise that we will do in the EOS model development. We can use those cubic equation of state. You can use those correlations with with the limited data that we have. And generally the limited data we have is we already know that from the gas chromatography, we have the measured molecular weight of the flashed oil and also the density of the flashed oil. So those are the surface oil densities we generally have, and we can try to match that data, those average numbers that we get from the lab, and come up with some kind of correlation that's tuned to this limited data that we have, and that correlation, giving the specific gravities of each component at ambient condition, can be used to tune the volume shifts. And that's something we will discuss in detail also when we will go through the EOS model development workflow. So yeah, so Curtis, do you have any comments here?
Yeah, I mean, the Javert and Young, they were with ARCO. They were one of the main, not operator, one of the main partners in development of Prudhoe Bay. Aaron Zick was there, who wrote the FaceComp software. And they were early adapters of the volume shift, but they were using the Peng-Robinson equation of state. So the values of SI or CI and given by Pindaloo were for the SRK. So they wanted to have some tabular values and a way to approximate the CI values for the Peng-Robinson equation of state. So they did this for various hydrocarbon families and gave a range for predicting that. Let's see. Yeah, and then but basically the way to go about getting it is not by correlation. It's to make the equation of state predict the specific gravity of each fraction in the C7 plus correctly. So no, that's it.
Okay. Yeah, so here we will just see how the volume shifts look like, for example, for Peng-Robinson and SRK equation of state models, and that's also something that we have seen before. So, for example, if we look at, for example, Peng-Robinson equation of state model, and then we have these volume translation parameters here. So what you see here that, for example, for methane, it has a very high negative correction. But on the other hand, for normal heptane, we have a very small overall correction. And the reason why it's and if we compare it with the SRK, you see that the methane has very small correction compared to, for example, normal heptane, and it is increasing as we go towards heavier and heavier fraction. And again, the reason is something that we went through yesterday, that when SRK equation of state model was developed, aim was to get the vapor pressure. Their major aim was to get these liquid phase densities of the lighter components right, which were C1 to, for example, C3, C4. But when Peng-Robinson equation of state model came, their main aim was to get these heavy oil densities right, which had these heavier fractions, a lot of heavier fractions. And that's why you see that this correction term, the volume translation, to get the right density for each component, it's smaller for the heavier fraction for Peng-Robinson, and it's smaller for these lighter fractions in the SRK equation of state model. And here we see that so that's this dotted line. That's something we saw before without the volume shift, how the densities are predicted for the liquid phase. And with the volume shift, we see that the two equation of state models are generally very comparable, the Peng-Robinson and the SRK, for example, for this pentane component. So yes, Hans?
I just have a question here. Maybe that's been a little confused, but in PVT sim, where we are using, they have something they call temperature-dependent volume shift. Yeah, I don't know if you come to cover that, because I have been told that if you have problem when you should tune an equation of state and you have problem to match the reservoir density and the stock tank oil density, you can use that. And I have seen it in if you're dealing with a very heavy oil, you have to use that. It takes 2 minutes to explain what I actually doing there. I know we can use that equation, but I don't know why. It's okay, you get better results, but I don't know why. But they call it temperature dependent.
Yeah. Curtis, do you have?
Basically, this volume shift term can be and is, in fact, varying with temperature. You see that on these, plots for the pure component, saturated liquid density and saturated vapor density. So the magnitude of that correction varies with temperature. The distance from the line in the data. Okay. So there's nothing wrong with that, and it's acceptable, and it's the way it is, no problem at all. Now, they, I think, have a linear form they force you to use for the temperature dependence between the volume shift and temperature. It's linear dependency. So they can build that for you if you have basically two densities at two different temperatures for the same composition for the same component, then you can get that temperature dependency. So it's expected. There's nothing wrong with it. Often we find it's not necessary. You can get reservoir densities within the desired 1 to 2 to 3%, and stock tank density is also within that same range. Occasionally we see that's not the case, and then we have ourselves not the temperature dependent volume shift, but we just have a separate set of volume shifts for surface temperature and for reservoir temperature. They just have it as a function. So it's completely okay to have it. There's nothing inconsistent with it. So
yeah. Any other questions here? We have an exercise here on this topic, and I will just go through it in the Excel. Okay, so I think we can. I just open the file. I will just show you, because it's the same exercise that we actually did yesterday, but now for this water, but now with it is with the volume shift. So I will just show you what is the difference between the two solutions. So I'm just opening the solved version actually. And so what we did yesterday, it was we have this volume shift. That's the S term. Now we must be familiar with what is S. That's the C over B. And that was 0. So we were not using any volume correction, and we found that this density is about 30% different than what is expected. And now we are in the next exercise, which is the second spreadsheet. We are going to use this volume translation and this value of 0.27319 and see how good or bad is the density predicted by this SRK equation set model with this volume translation. And we will be using this Penalou method, and according to Penalou method, you can do all your equation of state model calculations the same way as we did before. So we can have the same solution until here, where we calculated the z factors from the cubic equation of state model. So this was our liquid phase z factor, and this was the vapor phase z factor. And now we know that these are the wrong z factors, or these will give us the wrong values of the densities. So we have to do the correction on them before we calculate the individual phase densities. So we have seen the correction applied on a molar volume basis, so that's why we can calculate the molar volume first from the Z factor, and that's just simply this PV equals to NZRT. Knowing the Z factor, we can apply that equation, and PV equals to NZRT. That will give us the molar volume of the liquid phase, and same using the vapor phase Z factor, we can get the molar volume of the vapor phase. And now these have to be corrected with the volume shift, and yeah, so these are just the fugacities calculated from these old rules, and that's what the method is proposing, that you can do the vapor pressure calculation with these rules, and that should not be affected when you change or calculate the new volume shifts. Yeah, meaning that these fugacities of the liquid and vapor phase, they will change in the magnitude, but this constraint of having the equal fugacity, that will not be affected, and the vapor pressure will remain the same. The liquid phase molar volume with the correction, now it is very simple. So taking this B46, that's this cell here, that's the wrong quote unquote liquid phase molar volume, and minus so that this thing here, that's the C value, and the way the C is calculated is simply taking S times B. So we know that the S is C over B, so C is equal to S times B, and so that's done here. So that's the liquid phase Z factor, and the vapor phase Z factor, we use the same C and do the same correction here. And you can see there is a big correction on the liquid phase because the magnitude of the volume is small, but the magnitude of the volume for the vapor is so high that it doesn't affect too much the vapor phase molar volume. And we also know that the vapor phase densities are usually okay with the volume shift, without the volume shift, unless we go to very near critical conditions or very high pressure and temperature where vapors have very similar density as the phases, and there we will see the magnitude of the vapor volume will be smaller, and it will have more impact. The correction will have more impact on the correcting the densities or the molar volumes. So now we have these molar volumes. We can again calculate the Z factors. Now these should be the corrected Z factors, which we can calculate from the density, and again can use the PV equals to NZRT. We could have used the molar volumes directly for the density calculation, and the density, liquid phase density from this new Z factor with the volume translation. So that's now 0.91950, which is closer to 1 gram per cc. And in fact, we can change this volume translation to actually exactly match the density of the liquid phase at these conditions, which we think it's 1 gram per cc. So if I for example change it to 0.3, let's see what happens here. Yeah, so it's increasing 0.94. If I change it to, for example, 0.5, so it's too high. 1.2, 0.4, 1.06. We can actually do the solver, and then it will make our life easy. So we want this number to be equal to the value of 1 and not run the macro. Okay. I don't know what happened.
You have to take enable content.
Yeah, sorry. Didn't see that. Okay, so data solver, we need the value of 1 here, and then change the value of S. So that's this volume shift that can give us the exact density, which is about 1 gram per cc for the liquid phase. So you can see that the volume shift can be used to accurately match the density that at the given pressure and temperature. But and that's why that's what Curtis and Hans were communicating, that this volume shift can be temperature dependent property, because if I go to some other temperature, for example, and then calculate the density with the same volume shift, I may find that the density is not the same, and is not the same as the expected density or the measured density for water at that temperature and vapor pressure. And then I may need a different volume shift to match that density. Okay, so that was all on this exercise, I think. Okay, everybody, so you can start the session. So what we just went through was the volume shifts, and that's something we can also see on the EOS table that we have on this Wilson PVT. The EOS we are gonna develop and gonna use, and so that's this VS term. That's the dimensionless volume shift, which we represented as S, and you see that it's different for each component. And since it's an SRK equation of state model, you have small corrections for these lighter fraction, methane, ethane, propane, and this correction increases for these heavier fraction as we go towards the heavier and heavier fractions. And it's positive. And also was what I was trying to say before, that for each of these components we will have some estimate of the specific gravity. Don't see it here in this table, but when we develop the equation of state model, we will see how we can come up with the specific gravity or the densities of each component, especially for these heavier fractions, the C7 plus fractions. And those specific gravities, either you can have measured data for each component, like for example, a true boiling point distillation, or we can have some kind of correlation tuned to some kind of measured data, giving us the specific gravity of each component. And what these volume shifts are doing, we are forcing the equation of state model to exactly predict those densities at the pressure and temperature where they were measured for each component. The volume shift, or for example, this number here for C7, it will exactly guarantee that the given specific gravity for this C7 component in the equation of state model column, it will be exactly matched. So, and that's something we will discuss more, and we will go through the EOS model development presentation. That's the next on the agenda.
But just go back real quick, just a short comment.
Yeah.
Hopefully make it short. The magnitude of VS there.
Yeah.
The plus or minus. So, for example, minus, well, there's very few minus because it's SRK. But if it was Payne Robinson, you would have like a minus 0.2 for C1. Okay. But basically, that is the deviation fraction of a liquid density expected for that component. In other words, it's saying how much the uncorrected two-parameter equation of state would be in error of the density. So the C8 would be minus 15%. Minus 15% too low. The C19 or the C20 would be minus 30% in error, down for C20. So that number, the S number, the dimensionless volume shift factor, is an approximate representation of the error that the uncorrected volume shift would equation of state would have. So it gives you the magnitude directly. I mean, it's not exact, but it's an order of magnitude, and it changes for each component. Just kind of a curiosity.
Very good, Curtis. Yeah, so again, we can jump to the topic now. And yeah, so the next topic that we have is the equation of state models applied for the mixtures. We went through equation of state models, how we can use those EOS model for a single component. And now we know all the ingredients that are there in the equation of state model for pure component phase behavior calculation. We need the TC, PC, eccentric factor. We need volume shift for the density, and we also need molecular weight because that's used to convert the molar volumes into the volumes and or the densities. So now we will see how the same equation of state models can be applied for mixtures. So that's just a brief background of that's the first point, brief background on how the EOS models are applied for pure component. And when we need to apply these EOS models for multi-component mixture, then we use the same EOS model, but we use these average constants in the equation of state model. So there will be an average value of A, average value of B, and average value of C that will be used in the equation of state model calculation. Because we know that this A term here, that's a function of the small a. B term here, capital B, is a function of small b, and small a and small b are component dependent. So they are different for different components. And there is one capital A and capital B that goes into the equation of state model. So we need to calculate an average A and average B and average C based on the composition. So this averaging can be done using some kind of mixing rule, knowing the composition of the fluid, meaning that the amounts of different molecules present in that mixture. That's in a general term we are representing as U, and this UI could either be a vapor phase composition, which is YI, or it could be a liquid phase composition XI. So the mixing rule generally used for A averaging, that's this quadratic mixing rule, and quadratic mixing rule. So that's, we have two summations here, and then you have this is just representing the amount of each component, and then this is the Aij, that's this A value for the component I and J, and component I and J A value can be calculated knowing the A value of component I and component J, and then we have an additional correction term here. That's so this Kij, so that's the correction to this coefficient A here, Aij. Between the Aij component, that's the correction term, and then this Kij, that's the small k with Ij component. So that's the binary interaction parameter that we saw in the EOS table. So that's your second table in the equation of state model that we call BIPs, and you can see that this is one value between two components. So it's one value between a pair of components. And yeah, so again, Curtis, he can tell you the stories about why the correction term is introduced as 1 minus Kij rather than just a correction term that we like we saw that we have a correction term to the small a in terms of alpha, and then we have a reduced temperature, for example, in the Rayleigh-Kwong equation of state, and that this is just a correction term alpha, but the correction term here is not just the Kij, but it's 1 minus Kij. And in Curtis, he can tell you the stories. Curtis, do you want to comment on it?
Well, the story is a bit long, but basically the original introduction to the binary interaction parameter BIP was by Prausnitz and his co-worker or maybe student Chu. And when they originally did it, they used the term small l for also small Lij for the entire 1 minus Kij. They didn't use 1 minus Kij. They just had a correction term Lij. And Lij, basically, they found if it was slightly less than 1 or slightly greater than 1, would vastly improve the vapor-liquid equilibrium calculations of some binary systems. In special cases. So that Lij of 0.98 could have a big improvement on how accurately it was predicting different behavior. So when they were trying to get engineers to apply these small corrections, they're usually at the most Lij was plus or minus 0.9 to 1.1 at the largest. They were doing these courses back in the 60s, and calculators, hand calculators were just coming in. Maybe they're still using slide rules, and so these students that engineers they were trying to teach and make them use these Lij non-equal to 1, they would get to the calculation and they would say, oh, that number is 0.978. I'm tired. I'm just going to use 1. Okay. And they had a hard time getting him to actually use those numbers. So Prowsons apparently came up with the clever idea that we'll write it as Kij and the entire term is 1 minus Kij, thinking that any good engineer will never delete a number 0.021, right? And so that's basically why it ended up being the 1 minus Kij term. Yeah. So it can be a positive or negative term, just as Lij can be greater than or less than 1. It's normally less than 1, but it doesn't have to be.
Yeah, very good, Curtis. Thanks again.
Just a question for me to clarify. So I get this that within C1 to C6 you fix your vapor pressure, and then you use the volumetric correction to get your densities. But when you start going to heavier components, your vapor pressure is not really well known. It's a range, right?
Yes.
So then you end up with 2 variables. I mean, you have the volume correction that is kind of on an XY, let's say it's moving on an X. And then you end up with these binary coefficients that can move you on the Y. And you still respect the fugacity, basically. So how do you know which of the 2 to go?
You mean like which parameter to change, like volume shift or the binary interaction parameter?
Yeah, because when you have an uncertainty in vapor pressure, that means that you can also move the vapor pressure a bit. Yeah. And that will change the density.
Yeah.
So how do you know whether to correct on density or to correct on vapor pressure? How to tell on a C7 plus component.
Yeah. Curtis,
for the C7 plus components, the only point on the vapor pressure curve you know is the normal boiling point. So we usually tie into that and hang on to that. We kind of force, if you have a normal boiling point, you force it to be predicted by the equation of state. So you actually determine the alpha term or the M or the eccentric factors you like in order that the equation of state predicts the normal boiling point of a known C7 plus fraction, okay? So that's how we control the vapor pressure curve part, is knowing one point on the vapor pressure curve, namely the normal boiling point.
Okay, so yeah, because I was missing you need to anchor something, otherwise.
Yeah, you anchor it to that. That's how we do it, yeah.
Okay,
that's the most consistent way, yeah.
Yeah, thank you.
Yeah, and this is something we will also discuss when we're discussing the EOS model development, like in the next slide. We will go briefly into the detail of what Gerardo was asking here. So Yeah, and then so this binary interaction parameter, so it is between the two same component, it's actually 0, and it's also like a binary interaction parameter between, for example, C1 and C7 component is the same between C7 and C1 component. So that's also this case here. So that's why the binary interaction parameter, like if it's a table with just one like it's a half diagonal. I can show it here. Yeah. So you see here the binary interaction parameters in the whole table, and here it's 0 for all the C2 plus components. We generally use only C1 and C7 plus component, and the binary interaction parameters, it's if we make this diagonal here, so on the diagonal it will always be 0 value, because that's the binary interaction parameter between the two same components. So like, for example, this value or this value, this will always be 0, and the values that are on the top part of the diagonal, those will be the same values as bottom part of the diagonal. So essentially it's only this bottom part of the diagonal that you see in the binary interaction parameters. It could be, and those could be non-zero values.
Yeah, Bilal, just it's a normal. I've seen it in several reports where they say the binary coefficients between the lights and heavies, they are not matched, and that is in order to avoid to gain precision on extrapolations outside the conditions that we've done the equation of state. How does that relate? Is that a rule of thumb, or does it have any background to it?
When you said those are not matched,
they are not improved by matching. So basically, they are left to 1 or they are left to 0.
Okay. So you mean that no binary interaction parameters for example, C1 and C7 plus component?
Yes.
Yeah. And yeah, so that's Curtis, do you want to?
I think the only one singing that song is CalCep with the SRK, and they sing the song because that's the song they like. And if you have to have them, you almost always have to have them, even if it's small, between methane and the heavy components. And even for the SRK, they could be smaller than magnitude than the Peng-Robinson, but that they should be 0, exactly 0 is just it's a song. Now, having said that, what you could say is that you have to be very careful with having larger binary interaction parameters for the heaviest component with methane, because the PVT data you're fitting, large BIPs, and you don't know what large means, but contrasting BIPs, like if is it C29, what's the heaviest component here?
C26.
Let's say we have these BIPs here. So 0.0419 C1 to C5, which is about like Katzenfiersbody recommended back in '78. But if you need to fit a bubble point or dew point of this system, and you change the BIP of C1 to C26 plus, and it goes to 0.23, what they can argue, and they're probably right, is that that's dangerous to start doing predictions of MMP, of compositional gradient, of where that heaviest C26 plus component is really important. Its phase behavior, its fugacity, and you don't want a big jump in the BIP really anywhere within the table. The discontinuity, you'd like it to be fairly smooth everywhere so that you don't get strange behavior, and again, outside the range of data that you're fitting. So that could be an argument. And that it needs to be 0, of course, making everything 0, there are no contrasts. There's no discontinuities in bits, right? If they're all zero.
Yeah.
But that's kind of it's like tying your hands much more than you need to. You just need to make sure that there's no big contrast in bits in general.
Yeah. Okay. Thanks. Yeah, because that was a myth that I kept reading over and over, and I never got to the basics of it, right? Or why is that claim? Yeah. Thanks.
And just an additional comment on what Curtis said. So if you have generally, like when we develop equation of state models, and if we have a lot of PVT data, a lot of PVT samples, and good quality PVT data, so in that case, you can, when you're changing these binary interaction parameters, you can play a bit more with these binary interaction parameter values in tuning the EOS model, because then you have a very wide range of composition, pressure, and temperature space to tune your equation state model on. But if you have very limited data, then then you have to be very careful in changing these binary interaction parameters, because then you may get very strange behavior outside of the PVT data or composition, pressure, and temperature you have for tuning the equation of state model. And the other comment that these numbers have to be zero, like for SRK equation of state model, which PVT sim characterization generally have. So we have a good exercise on this at the end of this session today, and we will see why you should not have exactly zero binary interaction parameters even for SRK equation of state model. And as Curtis said, that the binary interaction parameters for SRK, it may be smaller in magnitude compared to Peng-Robinson, for example, for methane and C7 plus fractions, but still you need some small correction there.
Thank you.
Very good. So yeah, so we were here. So how the equation of state models are applied for the mixture, so we can see here that this average A is calculated with the A values of individual component by quadratic mixing rule. Then for average B, we have this linear mixing rule, and for average C, we again have a linear mixing rule. And these compositions, again, this can be a liquid phase composition or a vapor phase composition. So if we have, for example, two phases in a multi-component mixture, then we need to calculate this average A, B, and C for both phases. So some more information about the binary interaction parameters. These are just the same thing that we had been discussing to now, and just rule of thumb on what you expect from these binary interaction parameters to look at what are the expected magnitudes. So non-hydrocarbon to hydrocarbon bits, these are generally between these numbers. And in the SP monograph, you can see what are the recommended values between non-hydrocarbon to hydrocarbon BIPs for this H2S, nitrogen, and CO2 for SRK and Peng-Robinson equation of state model. So those should be the initial estimates of these numbers, and those should not be changed if you don't have any good PVT data measured with non-hydrocarbons, like with CO2 injection or nitrogen injection, for example. Then hydrocarbon to hydrocarbon bits, these are kind of the extreme values. And again, as Curtis was saying, that you can have a negative binary interaction parameter giving you this Lij, the correction term, greater than 1, for example. But generally, it's a positive. The Kij is generally positive, and the Lij is generally less than 1. Yeah, and one important comment, because the binary interaction parameter, that's again Kij, since it's one coefficient between two components, Kij, that's why it affects the K values of the two components simultaneously. And that's we will see in the next slide, and that's something very important to keep in mind, that if we have a binary interaction parameter of 0, and then if we start increasing the kind of binary interaction parameter towards a positive number, what we will see that if we have two components, a lighter fraction and a heavier fraction, the K values. So this is, again, not to confuse the two Ks. This is the capital K, this is a small k. So this is the K value of the lighter fraction. This is the K value of the heavier fraction, and you will see that they start moving apart from each other. And if we go in this direction where the Kij, the small Kij is negative, you will see that they start moving towards each other. So, and you can see from this figure that the Kij, the small Kij, the binary interaction parameter between two components, affects the K values of the two components simultaneously. Yeah. And this slide actually shows kind of, if you just look at this figure on the left, just forget about what is on the right. So if you look at here, so first, these are the figures that I took from Marcus Curtison's thesis, and his thesis was mainly on this effect of binary interaction parameters on the K values. Very nice work done by Marcus on his master's thesis, and now he's working with us here at Whitson. So on the left, what you see is how the binary interaction parameters affect the K values, and we have already seen how the K values look like. For example, for if these are just the two components. So again, this is the lighter component, this is the heavier component, and that's how the K value look like as a function of pressure, right? So this is, we have already seen. This is the convergence pressure, and at low pressures, the binary interaction parameters, the way they affect the K values is that if you, again, we saw before that if you have a positive K value, if you have the positive binary interaction parameter, or if you increase the binary interaction parameter in the positive direction, what you will see that the K values of these lighter and heavier fractions, they start moving apart from each other. So for example, with a positive value, it will be somewhere like this. And again, it will be somewhere like this. And they will move apart from each other. If we go into the negative direction, they will start approaching towards each other, the lighter and heavier K values. And at high pressures, which is mainly relevant to the reservoir conditions, the effect of binary interaction parameter, it can go in any direction. So we know that at high pressure, the K values are mainly function of this convergence pressure together with pressure and temperature. And this convergence pressure, it can move in any direction. It can move on the left side or the right side, depending on the temperature. So if you have a positive binary interaction parameter or a negative binary interaction parameter, you cannot tell exactly where this convergence pressure is going to move, affecting all the K values at high pressure. And it's mainly function of temperature, which we actually see on the figure on the right hand side. So what you see on the right hand side, this is again binary system, binary two component system, ethane and C7, for example. So this is the vapor pressure curve of ethane. This is the vapor pressure curve of C7 with their critical points here. And then in between, if we take this black dotted line here, so this is with Kij equals to 0. So if you don't have any binary interaction parameters, this curve here shows for different mixtures of C2 and C7, how the critical, like the critical of those mixtures look like. So that's one mixture, for example, of C2 and C7. That's another mixture of C2 and C7. And then we have, so these are the different mixtures of C2, C7, how their critical point, the TC and PC of the critical point looks like for the different mixtures with Kij of 0. Now, if we have a positive wave, that this red dotted line, so what you see here, maybe I should just zoom it a bit. So what you see here at this, okay, now I cannot write. Yeah, so what you see here at this point, that this point here, that the yeah, that's something we have already also discussed before, that the convergence pressure, if we are talking about the critical temperature, the convergence pressure is the same as the critical pressure, right? So all these are actually the convergence pressure for those binary mixtures. So what you see here, the red dotted line, that the convergence pressure or the critical pressure is lower than the critical pressure with the zero binary interaction parameter. So it means that it is moving to the left on this figure here. It's moving on the left. And if we go higher towards at higher temperature, then it changes the sign. So now it's moving to the right of the zero binary interaction parameter. That's the reference line for us, the dotted line, black dotted line. So now it's moving on the right hand side. Same if we look at this blue line, which is with the negative binary interaction parameter, and if we look at with reference to the zero binary interaction parameter line, you see that with the at temperatures lower than, for example, this temperature, it is moving to the right of the zero binary interaction parameter here. So it's moving here on this direction. And then same at higher temperature, it's moving in the other direction. So this, like how the convergence pressure is gonna move, and that's mainly function of temperature, and you don't know in which direction it's gonna move. But we know that this convergence pressure is affected a lot by small changes in the binary interaction parameter, and that's why binary interaction parameters are very effective in tuning the equation of state models, mainly changing or affecting the k values at high pressures. But again, you have to be very careful when you're playing with these numbers, because there are like very small changes in these numbers can have huge impact on the k values, and you may get very non-physical behaviors that you should not expect. And yes, Curtis?
Effective and dangerous.
Yeah. Effective and dangerous, yeah. That's very well said. So yeah, so what are the general guidelines on binary interaction parameters? So generally, the binary interaction parameters are used between methane and the C7 plus fractions only. So that was actually recommended by Carstens for Zabadi paper in 1978. That Curtis was referring to yesterday. So that was the first paper on the EOS model applications in petroleum, in the petroleum engineering discipline. That was right, Curtis?
Yes, that's correct.
Yeah. So in their paper, they were using this Pang-Robinson EOS model, and they said that if you use these positive numbers, small positive numbers, or binary interaction parameters between methane and these heavier C7 plus, you can get very accurate predictions of the measured k value data. So they have shown for a bunch of fluid systems how the measured k values were the predictions of measured k value data was improved by having very small binary interaction parameters value between C1 and C7 plus fractions. So these are just the details here. And then like when we develop equation of state models, generally we start with the binary interaction parameters correlated with this two correlation here. So that's the two correlation that's relating the binary interaction parameters with the critical volumes. So we need critical volumes, or you can also have critical z factors to estimate initially what are the binary interaction parameters for the different components, and generally we only do it for C1, C7 plus only, and so that is just an initial estimate for the binary interaction parameters, and it gives this correlation gives a very smoothly behaving binary interaction parameters for C1 and C7 plus fractions, and that is just a starting point for our initial EOS model, and then we see if we need tuning on those binary interaction parameters when we start working on EOS model tuning. So that's something we will also see, and we will develop the EOS models in the next session. For SRK equation of state model, you can start with a 0 hydrocarbon BIPs, or you can also start with this. You can start with the binary interaction parameter with the Q correlation, and later on you need to do some tuning. You may need to do some tuning on those binary interaction parameter values. So these are things that we. Again, Peng-Robinson versus SRK equation of state models. Now we have already gone through, if we have 3 parameters in the EOS model, so including the volume shift, so you have A, B, and C, including these 3, and if we have appropriate BIPs, and that's something we have found that you need slightly more positive BIPs in Peng-Robinson compared to SRK between C1 and C7 plus. You can get very good EOS predictions and very similar prediction between the 2 EOS models. And when we have this third parameter in the EOS model, the mixture liquid densities are also comparable between the 2 EOS models. So the 2 EOS models, in terms of the prediction, they are very comparable, and any EOS model can be used to model the reservoir and surface PVT data. And yeah, that's something we have also gone through a lot of times, that if you have PVT data available, we should try to use all the data that's available in the EOS model developing, and not just a subset of the PVT data. Yes, Gerardo?
Yeah, just a question in something I have no idea, so maybe the question is really silly. What happens when we know that we start developing solids on our fluid? Mm-hmm. Let's say we go through a phase change and we know we have either asphaltenes or wax coming out. How do we take that into account? Do we use this set of equations of states or something completely different?
Yeah, so you can when you want to start predicting these solid phases, the wax or asphaltenes, then you have other models that are meant to predict this solid liquid phase equilibrium, but those models are used in conjunction with the cubic equation of state model. Curtis, do you want to?
Yeah, that's exactly right. You use this model that's matched and tuned to vapor liquid equilibria data. That's a basis model that's used together with other models to do the wax asphaltene type predictions. So yeah.
So it's an add-on. I don't have to rebuild everything.
No, exactly.
Okay. Yeah.
At least the better models, the preferred models for solids modeling are starting point in the cubic calc.
But just one additional comment on this. So like, for example, if you want to have a good prediction capability of wax deposition, for example, then like the cubic equation of that model that you will be using in that case, it should be tuned to some low temperature measured PVT data, because we know that wax usually deposit at low temperature. So you should have some kind of vapor liquid equilibrium data, for example, CCE test done at low temperatures or something, some other measured data at low temperatures to match your equation of state models to that, to be more confident that that the cubic EOS will be giving reasonable variations at those temperatures when you start using it for VEX modeling, for example.
Thank you.
Very good. So so this is just a few additional slides on how the vapor liquid equilibrium calculations are done for mixtures. We saw these calculations, how they are done for pure component, and there it was only the vapor pressure that we were interested in, and the individual phase densities. And there it was very simple case. There was no need to have any K values, just using the equation of state model to predict the vapor pressure and the individual densities. But if we have mixtures, then what is the objective of doing the vapor liquid equilibrium calculations? The first one is for any given composition, pressure and temperature. We would like to know what are the number of phases. So either it's a single phase or does it exist in two phases? And if it's in two phases, then we would like to know what are the amounts of each phase. And also, if it's two phases, then what are the compositions of each phase? So we saw this. This is actually solved with the help of flash calculation, and we did it. I think the first day or second, I don't know. Maybe the first day we did the flash calculation. So this is with the help of the flash calculation, and also even this one, so the number of phases. Yeah, I think here there should be an additional thing, and that's the phase property. So meaning that you need densities, for example. So that here you get your equation of state model to be used to get those numbers, the densities of the phases, like the liquid phase and the vapor phase. And the constraints we have, we honor the material balance for each component, and that we saw in the Rechford rise. The other constraint we have is the thermal and chemical equilibrium. So the chemical potential, or you can also say the fugacity of each component in the vapor phase, it has to be same as the fugacity of each component in the liquid phase. And that's the function of the composition, pressure, temperature, and the molar volume, the vapor phase molar volume and the liquid phase molar volume that we get from the equation of state. So this is we get from the EOS calculation. This is we get from the flash, and we will see how in the next slide. So the workflow, it's just the condensed workflow. It can be very complicated, like when you start, if you want to program it. But this is like a general condensed workflow on how the vapor liquid equilibrium calculations are done for mixtures. So again, you need an estimate of the K values, and we will see how this estimate can be improved. But you can start, for example, estimate from the Wilson correlation and or phase stability test that was from this Michelson. So that's also given in the SP monograph. Once you have the estimate of the K values, you use the Rechford rise to calculate all these numbers that we actually did on the first day for the given total composition, pressure, and temperature. So this is your flash calculation. And you can see now that you need the K values, right? So for mixture, you need K values to do the phase, the vapor liquid equilibrium calculation. And then we use the that we get from here, so xi or yi, to calculate the EOS coefficients. So these are the average coefficients for the given composition, the average A, B, and C. And we calculate them for both vapor and liquid phases. And then we use the equation of state model to calculate the vapor phase and the liquid phase. Vapor phase and the liquid phase Z factors. calculate the fugacities of each component using the composition. And then we check that each component in the liquid phase and the vapor phase are the same. If this constraint is violated, like if they are not the same, then you have to update your K values. And there are different methods again to update how you can update the K values given in chapter 4 in the monograph. And if this constraint is met, then your solution is converged, and then you can jump actually to this step 7, where you get the modes of the vapor phase and the liquid phase and the compositions. So once this is true, it means your solution is converged, and it means that the flash calculation that was done by this time, it has given you the right amount of the vapor and the liquid phase of each phase. And from this step 4, you would have gotten the final values of the vapor and the liquid phase Z factors. And with these numbers, we can calculate, you can calculate, for example, the density of the vapor phase, density of the liquid phase. So now you know you have met all the objectives. So now you know what are the amounts of each phase, the compositions of each phase, and what are the properties of each phase. Okay, so I think we just look at this exercise, which is it's an Excel-based solution, because there is a lot of uninteresting work, because they let me just show you first, and you would understand what do I mean here. So let's go to day 3, and that's this exercise 13. If I open this Excel file, so in this Excel file we have 2 components, methane and normal decane. So we are doing this phase behavior calculation for this binary system, and you can see that there are a bunch of phase comp files, because we use the phase comp files to do these calculations without, for example, binary interaction parameters and volume shifts. And then we have volume shift but no binary interaction parameters, and then we have in this third case, that's C here, have the volume shifts and parameters both. And actually why we choose this C1 and normal C10, because we have I found like some measured data on this and this binary interaction parameter on this binary component system. So all the calculations were done in, for example, phase comp against the measured data with the 3 cases. So that's like the summary here. So we have the case A, that's the PR, that's the Peng-Robinson US model we have used. There are no volume shifts being used and no binary interaction parameter. That's case A. Then we have case B, where we have the volume shifts but no binary interaction parameters. And then the third case with both volume shifts and binary interaction parameters. The magnitude of the binary interaction parameter that was used, for example. And on the right here, so here this is the table showing you what are the measured, for example, so this is the density, the measured densities at given pressure and temperature, and then the calculated densities. And this table is without volume shift and binary interaction parameters. And then we have the saturation pressure calculation, again, measured data, calculated data at different temperatures. And on the right, we have this table is with both volume shifts and the binary interaction parameter. So this is case A and this is case C results. So if we look at, for example, just the plot of saturation pressure, you can see, the red points, those are the measured data. That's how the predictions look like if you don't have any binary interaction parameters. But if you have binary interaction parameters, then your saturation pressures are greatly improved. Same if you go to the densities. If you don't have any binary interaction parameters, the density, the more important thing is the volume shift. So without volume shift, that's how the densities look like, and with the volume shift, that's black line, and you can see how these densities are improved. And if you look at this summary table here, so yeah, just forget about these numbers here. Actually, let me just do this here. Just grade bias numbers. We will not discuss these here. So if we look at this first case without the volume shift and binary interaction parameter, we can see the percentage total error in the density calculation. That's about 4%. The saturation pressures are about 13% off. Now in case B, what we have done differently is just to add the volume shift. So now the volume shifts are non-zero, and we still have binary interaction parameters. And you can see that the predictions, the densities are improved. So you only see the difference in the density. The saturation pressure error is the same. And the reason, again, we discussed that with this Panaloo method, if you have introduced volume shift, it should not affect any phase behavior PVT calculation. So it should not affect and it should not affect your, for example, saturation pressure. And that's what we see here, for example. So this is the K value of C1. This is the K value of normal decay without volume shift, and these are the K values with volume shift. No change in the binary interaction parameter, and you see they are exactly the same because the volume shifts doesn't affect the phase behavior calculation. And in the third case, we have both volume shift and binary interaction parameters, and now we have the densities and the saturation pressure, so it's greatly improved from 13% to about 1%. And here you can see that the K values are now changed compared to the previous case. And what we should expect, because here you can see that the Kij, the binary interaction parameter, is positive, 0.05. So that's why if it's a positive number, then the K value of the fraction, the heavier fraction, they should depart from each other. And that's what you see here. The K value of the lighter fraction, it is increased, and this is decreased. So they are moving apart from each other. Yeah. So yeah, I think this was all actually in this exercise. And one other important comment. Important to know that the bubble point, like if we talk about just open the here. Do we have Paris? No? Yeah. If we have the bubble point, then the bubble point prediction is actually directly proportional to the K value of C1. So if the K values, and that's the capital K. So if the K value of methane is increasing, the bubble point prediction will increase. K value of methane is decreasing, the bubble point prediction will decrease. Similarly, for gas condensate, the dew point, this is inversely proportional to the K value of the C7 plus fraction. So if the K value of the C7 plus fraction is increasing, it means the dew point is gonna decrease, right? And if it's decreasing, the dew point is gonna increase. So that's why, like, if I have Kij, for example, 0, and if I move it to, for example, 0.05, for example, and this, let's say my lighter component, that's my component I, for example. It is my lighter component, that is, for example, C1, and my heavier component, that's my component J, is let's say C7, C7 plus, all the components that are heavier than C7. Okay, so what is gonna happen, that this K value, the K value of C1 is gonna increase, and the K value of C7 plus is gonna decrease with this positive binary interaction parameter. And what is gonna happen if I have a mix of bubble point and dew point samples? For example, in my EOS model development, and all the bubble points, they are gonna increase, right? And all the dew points are gonna increase. So all the saturation pressures, they will move in the same direction when we move the interaction in one direction. If we move the binary interaction parameter to some value less than 0, then the bubble points are all gonna decrease, and the dew points are all gonna decrease. Okay, so this was all from this session here. Yeah, and now, yeah, Gerardo, you have a question?
Yeah, Bilal, when we decide to, sometimes we take this decision to add a geothermal gradient into our equation of state. What are we actually doing?
You mean thermal gradient for the gradient calculation?
Yes.
Yeah. That's something we will discuss tomorrow when we will be discussing the fluid initialization, but I can just add a quick comment there. So when we do the fluid initialization calculation or the gradient calculation, the model that we actually use, that it's an isothermal model. So you assume constant temperature, and then you do this thermodynamic equilibrium calculation with depth. That's the model that is actually thermodynamically correct. But if you start adding these thermal gradients in the model, then you cannot use that isothermal model, and then there are different other models that are given in the literature, and those models, like according to Michelson, who is actually known as the godfather of thermodynamics, actually, according to him, that those models are like nobody has given like those models for like binary components. People have shown that those models work, but for actual petroleum systems, nobody has shown or come up with a case or like these models are thermodynamically correct and should work in all cases. So that's why like you can tune different coefficients in those models, like these heat diffusion coefficients in those natural data, but that doesn't necessarily mean that those models are correct and those are capturing the right behavior in your field.
Is there at least yeah, because I noticed that when we are trying to define the gas-oil contact by equation of state, right? That's a typical exercise. Now, is it something that says, okay, but if you are in less volatile fluids, it might improve compared to volatile fluids?
No, I don't think there is any literature or any paper on this that if you have such kind of fluid system, you should be using the fluid gradient calculation with thermal gradient. But again, I think Curtis, he can add his experience on that, and I think he has also he had good communication with Michelson, so he can also add his opinion and Michelson's opinion on using these thermal gradient models for fluid initialization, and how much confident you should be on those gradient calculation.
Thanks.
Okay.